Welcome to the Linux command line course. In this introductory lesson, we'll provide an overview of the course structure, its contents, and share some valuable tips to help you maximize your learning experience. Excited? Let's jump right in. At the heart of our teaching philosophy is making learning enjoyable, smooth, and efficient. With years of experience under our belts, we've refined our methods and crafted a course that sets you up for success. We've designed this course with bite-sized lessons, allowing you to digest the material easily and progress at your own pace. Studies show that shorter lessons lead to increased retention and engagement, ensuring that the knowledge you gain sticks with you for the long haul. We understand that some of you may already have experience with the Linux command line. That's why our flexible course structure allows you to skip lessons, covering material you're already familiar with. We recommend watching the first few minutes to confirm your understanding of the concepts, and if you're confident, feel free to hop on over to the next lesson. We believe in the power of example-based teaching. Every new idea is accompanied by a straightforward example that perfectly illustrates the material. This approach allows you to grasp new concepts quickly and intuitively. As the saying goes, an example is worth 1,000 words. Perhaps the most exciting feature of our course is the opportunity for hands-on learning. We've designed the course in such a way as to allow you to follow along with a Linux command line on your device, giving you an immersive experience that leads to a deep and intuitive understanding of the command line while also providing real-world experience. So, are you ready to dive into the world of the Linux command line? Let's begin. Welcome to the first lesson of this course. In this introductory lesson, we'll get familiar with the Linux operating system. We'll explore the unique features and advantages that make it the go-to choice for countless users around the world. So, let's get started. Linux is so popular that it's practically hiding in plain sight. It's the backbone of everything, from smartphones and smartwatches to smart fridges and even supercomputers. For example, did you know that Android, which powers millions of devices worldwide, is built on top of Linux? That's right. Every time you use an Android phone, you're secretly interacting with Linux. How cool is that? But what makes Linux so widespread? Well, it's because it's an outstanding operating system. For starters, it won't burn a hole in your pocket. Linux is free to use and distribute, making it an ideal choice for organizations and individuals looking to cut costs without sacrificing quality or performance. Another reason is its bulletproof reliability and top-notch security, all thanks to its open-source nature. The term open source means that the code behind Linux is freely available to everyone. This leads to a swamp of brilliant developers constantly reviewing and contributing to Linux's improvement, ensuring that those pesky bugs or sneaky security vulnerabilities are squashed faster than you can say, Linux. But wait, there's more. This collaborative approach allows people to create their own versions of Linux, also known as distributions. These distributions can be thought of as different flavors of the same operating system, each built upon the same underlying code. Well-known examples include Ubuntu, Red Hat, and Arch Linux. With so many distributions to choose from, Linux can be tailored to suit anyone's specific needs, whether that's running a simple web server or even a supercomputer. In this course, we'll focus on Ubuntu, the most popular distribution. However, the skills and knowledge you gain here can be applied to other distributions as well. Before we get our hands dirty with the command line, let's make sure you're all set up. We highly recommend opening a Linux command line on your device and following along with the course. This hands-on approach will provide you with a more intuitive understanding of the command line and help you retain the information better. As the saying goes, practice makes perfect. If you're feeling a bit lost on how to access an Ubuntu terminal, don't worry. Just head over to the Installing Linux section of the course. There, you'll find two methods for accessing the Linux command line, whether you're using a Windows or Mac OS system. Once you're all set, proceed to the next lesson where we'll begin our hands-on exploration of the command line. See you there. Welcome! In this guide, we'll walk you through the process of setting up a Linux command line on a Windows computer. By doing so, you'll be able to follow along with us throughout the course and gain hands-on experience with the command line. Before we get started, however, it's important to note that these instructions are tailored towards users running Windows 10 or later. If you're using a Mac or an older version of Windows, just hop on over to the next lesson, where we'll guide you through an alternative installation process. With that said, let's get started. Accessing a Linux command line within Windows is incredibly easy, thanks to a nifty feature called the Windows Subsystem for Linux, or WSL for short. WSL allows us to run a Linux operating system within Windows itself. It's like a text sandwich. All we have to do is open our Start menu and search for PowerShell. But wait! Don't just click on the result that appears. Instead, right-click it and select Run as Administrator. Within the PowerShell window that appears, type the following words: wsl.exe, followed by a space, 2 dashes, and the word install directly after. Once ready, press the Enter key to execute the command. The Linux installation process will now begin. This may take some time, so feel free to grab a snack, do a little dance, or simply relax and watch the magic unfold. Once the installation is successfully completed, you're good to go. If you encounter any errors, don't panic. Just proceed to the next lesson, where we outline an alternative installation method. Let's go ahead and close the PowerShell window and give our computer a quick reboot. With our computer refreshed, it's time to launch our shiny new Linux installation. All we have to do is open our Start menu and search for Ubuntu. You might notice a few more installation steps happening. Again, if any errors pop up, just head over to the next lesson. With the installation complete, we're prompted to create a new username for our Linux machine. So, let's go ahead and do that. Next up, we need to set a new password. Don't worry if the letters don't appear on the screen. Your keyboard is working just fine. This is a security measure that protects passwords from prying eyes. Re-enter your password to confirm. And voila! Time for a virtual high five. Your Linux installation is ready, and the world of Linux is now at your fingertips. So, head back to where you left off, and let's continue exploring the Linux command line. See you there! Welcome! In this guide, we'll walk you through the process of setting up a Linux command line on either a Mac or Windows computer. By doing this, you'll be able to follow along with us throughout the entire course and get your hands dirty with some real command line action. So buckle up and let's dive in. One of the most convenient ways of running Linux is by installing it within a virtual machine, or a VM for short. A virtual machine is a powerful tool that enables us to run an operating system on top of another. It does this by creating an isolated environment for our new operating system within our current one. But enough nerd talk. Let's see how we can set this up. First, we need to download an application that facilitates the creation of a virtual machine. Let's go ahead and open our web browser and search for VirtualBox. Click on the first link that appears, which should be the official VirtualBox website. From there, click the Downloads link from the sidebar. Next, we need to select the operating system we're using. Click on the Windows Hosts link for Windows or the Mac OS Hosts link for Mac. The download should start right away. While VirtualBox is downloading, let's also grab the star of the show, the Linux operating system itself. We'll be using Ubuntu Server, which is a specific version of the Ubuntu distribution. We chose this specific version of Linux because it's one of the most popular versions of Linux. You'll probably be using it throughout your career for hosting websites, databases, email servers, or other applications. This means that throughout this course, you'll gain real-world experience in the specific version of Linux you're likely to be using. How cool is that? Now that we've hyped up Ubuntu, let's go ahead and download it. First, search for Ubuntu Server. Click on the first link that appears, which should be the official Ubuntu website. Look for the latest version of Ubuntu Server and click the Download button. The download should begin shortly. While that's downloading, let's finish setting up VirtualBox. With the VirtualBox installer downloaded, let's simply click on it to launch it. From here, let's follow the on-screen instructions to install VirtualBox on our computer. Hint: it mostly involves clicking the Next button a few times. With our installation complete, just hit the Finish button, and presto! VirtualBox springs to life, ready for action. For our next step, we'll be needing our download of Ubuntu, so let's make sure it's complete. And it's done! Let's head back to VirtualBox and create our virtual machine. Within VirtualBox, click on the New button. In the window that appears, we need to type in a name for our virtual machine and to specify the location of the Ubuntu file we just downloaded. Afterwards, don't forget to select the Skip Unattended Installation option and then click Next. On this page, we need to allocate some sweet resources to our virtual machine. We recommend at least 2 GB of RAM and 1 or 2 CPU cores. In the following page, we can leave the default settings and move on. Here, we see an overview of the parameters for our virtual machine. Let's just click the Finish button to confirm, and we're off to the races. Our virtual machine has been created. VirtualBox will now automatically start the virtual machine for us. Our machine has now sprung to life. Let's close this notification box. Hit Enter to seal the deal. It might take a few minutes for it to boot up and perform some initial steps, so feel free to grab your favorite snack in the meantime. Here, we're asked to select the language for our Linux computer. Let's close this notification box and use the up and down arrow keys to select our preferred language. Hit Enter to seal the deal. For the next few pages, just press Enter to stick with the default options. For this page, we need to use the down arrow key to navigate to the Done option before pressing Enter. Let's do the same on this page as well. In the dialog that appears, we need to select the Continue option and use Enter to confirm. Now, let's get personal. Enter your name, a name for your computer, a username, and a password. Avoid spaces and uppercase letters here. We'll explain why in a following lesson. Make note of the username and password you used. We'll be needing it later to log into our system. Once ready, select the Done option and press Enter. For the following few pages, select the Done option as needed. For the last few pages, we need to navigate to the Done option before pressing Enter. And that's it! Our Ubuntu installation will now commence. It might take some time to complete, so feel free to grab another snack or just kick back and watch the magic happen. Through the power of video editing, we'll fast forward this process for you. Installation complete? Awesome! Now, let's choose the Reboot Now option. Don't sweat it if all the text that pops up looks like ancient hieroglyphics. You don't need to decipher it unless you're a Linux programming prodigy. If the login prompt doesn't appear after a while, just give Enter a friendly tap. Time to enter your credentials, which you hopefully haven't forgotten. When it comes to the password field, don't be alarmed if the characters don't appear on the screen. Your keyboard's not playing tricks on you. This is just a sneaky security measure that keeps passwords safe from prying eyes. Virtual high five, anyone? Your Linux installation is good to go, and the captivating world of Linux awaits you. Remember, whenever you need to shut down your virtual machine, simply type Power Off into the command line and press Enter. The virtual machine should shut down at once. To get it up and running again, just head to the VirtualBox interface and give your virtual machine's name a double click. Ubuntu should be back in action in no time. Now, all that's left to do is head back to where you left off in the course, and let's continue exploring the Linux command line. See you there. Welcome to today's lesson. Today, we'll explore the Linux command line, demystify the concept of commands, and learn how to execute them like a pro. Are you ready? Let's begin. Let's get to know the Linux command line interface. This is where countless hours will be spent, filled with both the joy of learning and the thrill of discovery as we unravel the mysteries within. Get ready to learn all about this powerful and versatile tool. Our first stop, a look around the various elements that make up this interface. The first few lines greet us with a welcome message and display various pieces of information. At the very top, we can see details about the specific distribution we're using, along with other relevant data. As a beginner, you don't need to worry about comprehending all these details just yet. We'll ease into them in later lessons. Next, we're treated to highlights of different applications, tools, or services related to our operating system. These tidbits are designed to inform us about new tools, updates, or features that can enhance our overall experience. As we reach the end of the welcome message, we encounter instructions on how to disable it. While these instructions might seem cryptic now, rest assured that you'll be able to understand them in due time. Just beneath the welcome message, we can see what we call the command prompt. This is where the magic happens. It's the space where we can type various commands and instruct our operating system to perform one task or another. Before we dive into the world of commands, let's break down the elements of the command prompt. First up, we have the username of the account currently logged into the system. Like other operating systems, Linux supports multiple user accounts, which we'll explore in a later lesson. Next, the @ sign stands proudly as a separator between the username and the computer's name, also known as the host name. This acts as a unique identifier for our computer. Next up, a colon steps in as another separator, leading us to the tilde punctuation mark, or as some call it, the squiggly line. Don't worry about this for now. We'll learn all about it in an upcoming lesson. Finally, the $ indicates that the prompt is ready to accept a command. What exactly is a command, you ask? Simply put, commands are specific words that we can type into our terminal to instruct it to carry out certain actions. Think of commands like miniature applications that execute specific tasks. Let's see what they look like in action. The first command we'll use is called ping. This handy utility helps us troubleshoot network and internet connectivity issues. Let's put it to work. All we have to do is type ping with a lowercase p, followed by a URL such as google.com. With a tap of the Enter key, we set our command in motion. As you can see, ping constantly attempts to communicate with our destination in order to determine whether it's reachable or not. A response indicates that we can reach the destination, and therefore we have a working internet connection. It's similar to how you know you're connected to the internet when you successfully open a web page. As ping works its magic, it reveals various information, such as the duration of each interaction. To stop ping from communicating with the destination, press the Ctrl and C keys on your keyboard. The C stands for cancel and is used to signal to our command line to abort the currently running operation. Once the operation stops, ping provides a few more statistics about the interactions that took place. Quite the spectacle, wouldn't you agree? If you're not familiar with all this networking terminology, don't worry. The purpose of this lesson is to teach you about commands. We used ping as an example because it not only looks fancy, and you can brag about it to your friends, but also because you may find it genuinely useful in the future. It's important to note that commands in the Linux command line are case sensitive. This means that typing ping with an uppercase P wouldn't be recognized by our terminal. Just for fun, let's give it a try. As expected, it doesn't work. Helpfully, our command line displays other commands that it thinks are related to what we're looking for, including ping with a lowercase p. How awesome is that? You not only learned what commands are, but also how to troubleshoot internet connectivity issues. Congratulations! Here are the key takeaways from this lesson. The command prompt is the space where we can type in various commands. It displays information such as the currently logged in user and our computer's name. Commands are specific words that we can type into a terminal to instruct it to carry out certain actions. Think of them like miniature applications that execute specific tasks. Commands in the Linux command line are case sensitive. If you're having trouble getting a command to work, make sure to double check the casing. I hope you enjoyed this lesson, and I look forward to seeing you at the next one. Welcome to another lesson. In this lesson, we're going to explore how to customize the behavior of our commands by using arguments and options. So, fasten your seatbelts and let's jump into the action. Remember in the previous lesson when we used the ping command to determine whether we're connected to the internet? Let's refresh our memory by taking a look at the command we used. Ping is obviously the name of our command. Google.com is what we refer to as an argument. Arguments allow us to pass information and provide context to commands. In this example, our argument provides the ping command the necessary information to carry out its task. Arguments can be either mandatory or optional. In this case, specifying a destination is mandatory, because without it, the ping command wouldn't know which destination to communicate with. However, not all commands require arguments to function. In fact, some may not accept arguments at all. To demonstrate, let's take a look at a command that does not need any arguments to function. Drum roll, please. Introducing the PS command, which is short for process status. A process refers to an active, running instance of a program within the operating system. In simpler terms, processes are applications that are currently being executed. The PS command conveniently displays all the processes on our computer. To see it in action, let's type PS in our terminal and press Enter. Awesome! Our computer's processes are now on display. Let's decode these cryptic columns. PID showcases the unique identifier for each process. TTY reveals the name of the terminal associated with the process. Time indicates the duration each process has utilized the computer's CPU. And lastly, CMD presents the command that initiated each process. If you don't recognize these processes, don't worry. We'll delve deeper into them in a future lesson. Notice that the PS command didn't require any arguments to function. In fact, it doesn't accept any arguments at all. That doesn't mean we can't customize its behavior. To do so, we need to use something called options. Options, also known as flags or switches, are specific letters or words that can be typed after a command to modify its behavior in some way. For instance, by default, the PS command doesn't include background applications in its output. To display every process, we need to use the PS command followed by the E option, where the lowercase e stands for everything. Options, like the one we're examining here, typically start with a single hyphen. This symbol denotes that we're specifying an option and not an argument. Let's give it a try. Awesome! The list of processes now features many more applications. Keep in mind that different commands require different options. They're not one size fits all. For example, the E option might perform an entirely different function for another command, or might not be recognized at all. So, how did we know that E is a valid option for the PS command? Did we randomly type letters until something worked? Nope. We consulted something called the manual pages. But let's not get ahead of ourselves here. We'll explore these in our next lesson. When specifying options, it's important to remember that they're case-sensitive, meaning that E with an uppercase E might not be recognized or could be misinterpreted. To demonstrate, let's try it and see what happens. Uh-oh, error message. Just as we thought, the E option with a capital E doesn't exist within the PS command. Now that we've got a handle on options, let's mix things up a bit. Within a command, we can specify more than one option to further customize its behavior. To demonstrate, Let's type our command just like before, but this time let's also include the F option, which stands for full format and makes the PS command display our processes in a format that includes even more juicy details. An alternative syntax is combining all of our options under a single hyphen. This makes our options look neater and makes quickly identifying them easier. With our command dressed to impress, let's hit enter and watch the magic unfold. Amazing! The output is now bursting with information about each process. Don't worry if it seems like hieroglyphics for now. Remember, you're still learning the ropes. Get ready for a plot twist. Options sometimes need arguments themselves. These are referred to as option arguments or parameters. One example of such an option is U, which stands for user. This option allows us to view the processes related to a specific user. To specify a user, all we have to do is type its name after our option. In this case, this username serves as the argument for this option. Let's see it in action. Ta-da! Our command now only shows the applications related to this specific user. Here's a fun fact. In the command we just executed, we could have typed user instead of the letter U. This is what we call the long form of an option. Long form options, such as this one, are usually preceded by 2 hyphens instead of just 1. Let's see it in action. As predicted, our command works like a charm. Some commands only accept the short form of an option, while others accept both. Whether the long or short form of an option is required depends entirely on the specific command. In our case, the PS command accepts both the long and the short form of this particular option. Wow, that was a lot. We hope you're not overwhelmed. Don't stress about memorizing all the different syntaxes and ways to specify options and arguments. They'll become second nature the more you spend time on the command line. For now, let's just focus on getting a feel for what options and arguments look like. To give you a hand, let's recap what we learned this lesson. Arguments allow us to pass information and provide context to commands. Some commands require them in order to function, while others do not. Options can also be used to modify the behavior of a command. But unlike arguments, they're usually preceded by a single or double hyphen, depending on their form. Options themselves often require arguments, which are called option arguments or parameters. I hope you had a blast during this lesson, and I can't wait to see you at the next one. Welcome to another lesson. Today, we'll learn all about file paths and discover how they allow us to effectively manage the files and folders within our computer. Let's dive in. As you probably already know, using an operating system typically involves interacting with the various files and folders within it. And while on a Windows machine you can just double-click on a file or folder to open it, things work a bit differently in Linux. Since we don't have the luxury of using a mouse, we need some way of telling the terminal which files and folders we want to interact with. This is where file paths come into play. A file path is essentially an address that describes the location of a file or folder within our system. Here's what they look like. File paths, such as the one we're looking at here, are made up of a series of names separated by slashes that help us pinpoint specific files or folders within our computer. The files and folders on our computer are organized using a hierarchical structure, with each folder nested within another folder. Starting from the very end of our path, we have the name of our item, and each name before that represents the folder it's located in. So, in our example, this path tells us that the cat.png file is located inside a folder named Pictures, which in turn is nested within a folder called Home. It's important to note that even though they're called file paths, They can describe the locations of both files and folders. We'll see what that looks like in just a bit. The keen-eyed among you may have noticed that the slash at the beginning isn't preceded by the name of a folder. Like we said before, slashes are used to separate words. So, what's this lonely slash doing here? Well, this slash represents the starting point in our system. As we mentioned earlier, the files and folders in our computer are organized in a hierarchical structure. As a result, we have a starting point from which everything else originates. This base, or starting point, is referred to as the root folder. Think of it as the main folder that contains all the other folders in our system. It's called the root folder because it metaphorically resembles the base of a tree, from which all branches, or in our case, folders, stem from. In a path, the root folder isn't represented by its name like most other folders, but rather by a single slash at the very beginning. In our example, this indicates that the home folder is nested within the root folder. Don't worry if the concept of the root folder seems a bit abstract right now. We'll delve deeper into it in subsequent lessons. Now that we've got the basics down, let's see how paths are used within our terminal. Like we said before, using an operating system often involves interacting with the files within it. To facilitate this, our terminal focuses on a specific folder at any given time, allowing us to manage the files within that folder with ease. To illustrate, let's figure out where our terminal is currently focused on. To unravel this mystery, we need to use the pwd command, which stands for Print Working Directory. The term directory is interchangeable with folder. So as you might have guessed, this command simply displays the folder our terminal is currently associated with. Let's give it a shot. Here it is. Let's dissect this path using our newfound knowledge. At the very end of the path, we have the name of the directory we're currently in, and each name before that specifies the folder it's nested within. In this case, we find ourselves in a directory named after our username. This folder is located within the home directory, which, in turn, is nestled within the root directory, as represented by the slash at the very beginning. You might be wondering, why is this directory named after our username? By default, Linux creates a folder for each user within the /home directory, named after their respective usernames. This folder is called the home directory for each user, which explains why it's nestled within the /home directory. By giving each user a separate directory for their files, we can ensure that they're segregated and organized neatly. It's important to note that whenever we log in, our terminal will always be focused on our user's home directory by default. How thoughtful! As we mentioned earlier, having the terminal focus on a specific directory allows us to easily interact with the files and folders contained within it. For instance, let's take a look at the contents of our current directory. To do so, we need to use the ls command, which is short for list or let's see, whichever tickles your fancy. Let's put it to work. No output. This means that our current directory is completely empty. Bummer! But don't fret, we'll explore a more populated directory in the next lesson. And that brings us to the end of today's lesson. If the concept of paths still feels a bit unfamiliar, don't worry. Transitioning from managing files and folders through a graphical interface to using paths and commands in a terminal can be a significant change. But rest assured, this lesson was just the appetizer. As we move through the upcoming lessons, you'll be able to use the terminal to perform all sorts of tasks. For now, let's recap our key takeaways. A file path is simply a series of words separated by slashes that help us pinpoint specific files and directories within our file system. The root folder is the starting point in our system and contains all other folders. In a path, it's represented by a single slash at the very beginning. For the Linux terminal to effectively interact with the files in our computer, it needs to be directed toward a specific location within our computer. I hope you found this lesson both enjoyable and informative, and I look forward to seeing you in the next one. Welcome to this lesson on navigating the Linux terminal. Today, we'll master the art of accessing any directory with ease and confidence. So, let's get started. In our previous lesson, we discovered that the terminal is always focused on a specific directory, allowing us to effortlessly interact with the files it contains. By default, this is our user's home directory. But what if we want to view or interact with files in another directory? No worries, the terminal has us covered. With a simple command, we can teleport our terminal to any directory we want. To demonstrate, let's say we want to navigate to the root directory. To do this, we need to use the cd command, which is short for change directory. Next to it, we need to specify the path of the directory we want to navigate into. As we learned in our previous lesson, the root directory is represented by a single slash instead of its actual name. Let's give it a spin. To verify our success, we can employ the pwd command, just like we learned in our previous lesson. Success indeed! The single slash confirms that we're now in the root directory. Now that we've arrived, let's take a look around using the ls command. Awesome! The contents of our current directory are now on display. If you're wondering what the various colors signify, blue is for directories, while other colors represent various types of files which we'll learn more about in the following lesson. So, what exactly are we looking at here? The files within our system are meticulously organized based on the items they contain and their respective purpose or function. For example, you might recognize the home directory, which contains each user's personal home directory. We can see several other directories as well, but let's save those for the next lesson as well. Now that we know the fundamentals of navigating within the command line, let's put our skills to the test by diving into the home directory we just discussed. Can you figure out the command we need to use? Put on your thinking cap. You have 10 seconds. Ready, set, go! Here's the answer. First, we need to use the cd command, followed by the path of the directory we want to navigate into. Since the home directory is located within the root directory, its path is simply a slash, which represents the root directory followed by the word home. Easy as pie, right? Just remember, the Linux terminal is case sensitive, so make sure you type home with a lowercase h. With our command ready, let's hit that enter key. To figure out if we were successful, we need to use the pwd command once again. But wait, take a look at the command prompt, specifically the text following the colon punctuation mark. The terminal conveniently displays the path of the directory we're currently in. This handy feature allows us to effortlessly identify our current directory without resorting to the pwd command. In this case, it confirms that we've successfully navigated to the /home directory. How cool is that? From here, let's unleash the ls command to explore the items within. As we touched upon in our previous lesson, Linux automatically generates a directory for each computer user, named after their username, within the /home directory. This structure ensures that each user's files are organized and kept separate. In our case, there's only one user, and the directory named after it is known as the home directory for this specific user. Let's step inside. As always, we need to start with the cd command, followed by a slash to represent the root, since that's where the home directory is located. Directly after, let's add the home directory itself, along with another slash and the name of our user's home directory. Easy peasy, right? While this command would work perfectly well, there's a nifty trick we can use to save ourselves from all that tedious typing. Up until now, we've been using full or absolute paths, which describe an item's location starting from the root directory all the way to the item itself. However, in this case, we can use something called a relative path instead. Relative paths describe an item's location not from the root, but from our current directory. To create a relative path, all we need to do is subtract our current working directory from our target path. We can also omit the slash since we don't need a separator. This leaves us with just the name of the directory we want to access. Pretty cool, right? In practice, this means that whenever we need to interact with files in our current directory, we can simply use their names rather than their full paths. No more typing marathons. It's important to note that the terminal's ability to focus on or associate with a specific directory is what enables the use of relative paths. By providing this context, the terminal allows us to exclude our current directory from an item's path. If the terminal didn't have this capability, we'd be forced to use absolute paths all the time. Talk about a nightmare. Having expressed our gratitude to the terminal, let's go ahead and execute our command. To determine whether we were successful, we can simply glance at our command prompt, just as before. What do we have here? Instead of our current directory, the tilde mark is displayed. That's because this squiggly line is an indicator that we're located in our user's home directory. In other words, it represents our user's home directory in a shorter and more concise manner. This means that we've successfully arrived at our destination. That's a wrap, folks. As an exercise for this lesson, head to your root directory and start exploring. Be sure to use both relative and absolute paths. In the meantime, here's a quick recap of what we learned. Use the cd command to change the directory the terminal is located in. Once there, use the ls command to view the items contained within. The terminal always displays the current working directory in the command prompt. If you see a squiggly line, that represents the path to the current user's home directory. A relative path is simply the subtraction of our current directory from the absolute path of an item. In practice, this means that we can refer to items in our current directory directly by their name. I hope you had a blast during this lesson, and I can't wait to see you in the next one. Welcome to our next lesson. Today, we'll embark on a tour of our file system. We'll uncover its organization and snoop around various directories. Let's get started. As you may recall from our previous lesson, we briefly mentioned that our system's files are neatly tucked away in different directories, each serving a specific purpose or function. To gain a deeper understanding of how our system is organized, let's delve into our system's directories and uncover their secrets. Let's kick off our journey by taking a look at the contents of our root directory. Rather than navigating there, we can simply instruct the ls command to display its contents by providing its path as an argument, which, as you might recall, is represented by a single slash. We've already learned all about the home directory in a previous lesson, so let's not dwell on the past. Instead, let's shine the spotlight on the bin directory, which stands for binary. No, it's not a place to store recyclables. The name refers to the specific types of files this directory stores, which are known as binary files. These files are meant to be run as programs, similar to .exe files in a Windows system. They're called binary because the data they contain consists of ones and zeros, as opposed to other data types, such as text. So, let's take a peek inside this directory using our trusty ls command. Wow, that's a lot of files. Some names may ring a bell, like the PS file we can see here. But hold on, why do these files share their names with commands? As we discovered in our previous lesson, commands are essentially small applications. So, when we run the ps command in our terminal, it's this very file that springs into action, much like double-clicking a .exe file in a Windows system. Pretty cool, right? You might be wondering why these executable files seem to be playing hide-and-seek with their extensions. Well, Linux users are a savvy bunch, and they're expected to know the type of data a file contains, and use the appropriate commands or applications to handle them accordingly. For example, they'd use a text editor to open a text file, rather than double-clicking on it and letting the system decide which application should be used to open it. To aid with this, some Linux files occasionally do have extensions, but only for informational purposes and user convenience. These extensions don't perform any other functions. They're simply considered part of a file's name. But what about files that don't have extensions? How are we supposed to know what data they contain? Fear not. The file command comes to our rescue. This command can be used to determine the type of data a file contains. Let's put it to the test. All we need to do is type the file command, followed by the path of our file. For this example, let's use the ps file we looked at earlier. Since this file is located within the bin directory, which is in turn situated within our root, its absolute path is simply a slash to represent the root directory, followed by the bin directory, another slash, and the name of our file. Let's give it a go. Don't sweat it if most of this looks like ancient hieroglyphics. You're not meant to decipher it unless you're a specialized Linux programmer. What interests us are the first few words, which indicate that this file is indeed an executable. In a similar way, we can use the file command to identify the type of any file. But wait, there's more. In addition to using the file command, a quicker way of identifying the type of data a file contains is by observing the colors from the output of the ls command. You're already familiar with blue for directories, but we also have green for executables, white for text files, and various other colors for different system files that we'll explore in future lessons. With that in mind, we can deduce that the bin directory is mostly filled with executable files. How cool is that? Now that we know all about the /bin directory, let's take a look at some other directories as well. Starting with the /etc directory, which is short for etc. You know the drill. Let's use the ls command to take a peek within it. This directory primarily contains files that store settings for various system components or hold other essential information. Files containing settings are called configuration files and are typically denoted by the .conf extension. By fine-tuning these configuration files, we can dictate how the various components of our system function. There's a good chance you'll find yourself wandering through this directory at some point or another, looking to edit one of those files or view their contents. But remember, with great power comes great responsibility. Don't mess with these files unless you know what you're doing. Thankfully, we haven't learned how to edit files just yet. Onward to another directory you'll likely encounter throughout your journey with Linux, the /usr directory, which is short for user. As always, let's use the ls command to check it out. This directory has a lot in common with its cousin, the /bin directory, as it also stores various executable files. The key difference is that while /bin houses only the most essential binaries, this directory stores executables for a wide range of applications. Specifically, binaries are stored in the bin subdirectory we see here. The /usr directory also houses various resources needed for our software to function, hidden away within the rest of these subdirectories. Don't worry about these just yet. We'll dive deeper into them when we learn how to install applications. While it's unlikely that you'll need to interact with the rest of these directories, let's give them a quick hello with the ls command. First up is the /media directory, which contains directories that represent removable media devices. You know how when you plug in a USB drive in a Windows system, a new directory appears for you to click on? In Linux, this is where that directory pops up. By navigating here, we can access all the removable media we've plugged into our computer. Another directory that might have drawn your attention is a directory called root. This directory, not to be confused with the root directory we're currently examining, is the home directory for a special type of user account called the root user. Why is it not located within the /home directory? Well, since the root user is kind of a big deal, having their directory separated helps ensure its isolation and security. But let's not get ahead of ourselves. We'll dive into this mysterious user in a future lesson. The remaining directories here mostly contain various types of system files, which we'll explore throughout this course. So, for now, don't worry about them. One key point we want to emphasize is that we don't want you to spend time trying to memorize all this information. What we want is for you to have an idea of what the purpose of these directories is. As you continue to use the command line, everything will come naturally to you. In the meantime, let's revisit what we learned in this lesson. Extensions exist in Linux for informational purposes and user convenience, but they do not perform any other function. To quickly identify the type of data a file contains, use the file command, or take a look at the coloring of the ls command. The /bin and /usr directories store executable files and other resources for our applications. The /etc directory stores configuration files related to various components of our system. I hope you had a blast exploring the file system with me. Can't wait to see you in the next lesson. Welcome everyone! In this lesson, we'll dive deep into the inner workings of our operating system and uncover the various components within. Are you ready? Let's go! Over the past few lessons, we've become familiar with various commands we can use within our terminal to accomplish a variety of tasks. But, have you ever stopped to wonder how the text we enter into our command line gets translated into specific actions performed by our operating system? To better understand this, let's zoom in on the nuts and bolts of the Linux operating system. At the very surface, we have the command line. It may come as a surprise, but what we're looking at here is merely an interface that accepts and displays text. The processing and decision-making is managed by several other components, which we'll talk about in just a bit. This interface comes in many different flavors, depending on the distribution of Linux we're using. Just as there are many web browsers to choose from in a Windows system, like Chrome or Firefox, Linux offers a multitude of terminal interfaces. So, how do we figure out which terminal we're currently using? All we need to do is use the following command. Don't worry too much about what this command is and how it works. All you need to know for now is that it prints the value of a variable which contains the information we're looking for. Let's give it a try. The output of this command reveals the terminal interface we're currently using. In our case, we're working with an Xterm terminal, which is one of the most popular terminal interfaces. Different distributions might come with different terminal interfaces. Try accessing a terminal on a mobile phone, a video game console, or even a smart fridge, and type in the above command to see what terminal you end up with. Have fun! Once you're done playing around, let's continue our journey into the Linux operating system by going one level deeper. As we mentioned earlier, the command line interface is simply a tool for accepting input and displaying output. The brains behind this operation are handled by something called the shell. Think of the shell as an interpreter between us and the operating system. It takes our commands and translates them into actions for our operating system. For example, when we execute a command such as ps, the shell locates the corresponding file within the /bin directory and runs it on our behalf. This allows us to communicate with our operating system by using simple commands instead of dealing with the complexities of our operating system directly. But that's not all. The shell also serves as a safeguard by limiting our ability to perform certain actions. This helps reduce the risk of users accidentally compromising the system's security or exposing it to potential threats. Hence, why it's called a shell. It acts as a protective layer between the user and the operating system. How cool is that? Shells designed to work with a command line interface are known as command line shells. These shells are specifically made to interpret the commands we enter into our interface and translate them into actions for our operating system. However, some Linux distributions come with a graphical user interface instead of a command line interface. For these systems, a different type of shell is employed, known as a graphical shell. Instead of interpreting commands, graphical shells interpret user actions on the graphical interface, such as clicking a button, into tasks for the operating system. For instance, you might have heard of Ubuntu Desktop, which comes with a graphical interface and, consequently, a graphical shell. On the other hand, Ubuntu Server, which we're using now, features a command line interface and employs a command line shell. Speaking of our shell, it's important to note that just like there are numerous terminal interfaces, there's also a variety of shells developed by different developers. To identify the one we're using, we need to type the following command. Once again, don't sweat the details of this command. We'll get into that in a future lesson. For now, let's execute it and see what shell we're working with. From the output, we can see that in this case, we're using a bash shell, which is among the most popular command line shells. Just like most other applications, the code for our shell is stored within the /bin directory. Let's use the ls command to take a peek. To locate the file named bash, we need to either scroll up using our mouse or by pressing the Ctrl, Shift, and Up keys on our keyboard. And there it is. This is where all the code that makes up our shell resides. Fascinating, right? We've uncovered the secrets of terminals and shells, but now it's time to dive even deeper. To carry out various tasks, the software within our system needs to harness the power of our computer's hardware. For example, for the ps command, to generate a list of all the processes in our computer, it needs to employ our computer's CPU, memory, and other components. This process is facilitated by a crucial component called the kernel. The kernel is the core, or the brain of our operating system, acting as the middleman between the hardware and the software within our system. The kernel's responsibilities include allocating resources like CPU time and memory to various processes in our computer, as well as managing requests from the shell or other applications. In essence, it ensures that all the hardware in our computer is effectively utilized to accomplish any task required by our commands or applications. The kernel is a fairly advanced concept, so don't worry about mastering it just yet. For now, all you need to know is that our commands and applications work hand in hand with the kernel to make use of the hardware in our system and perform various tasks. And that's a wrap, folks. Let's do a quick recap of today's lesson. The command line is an interface that allows us to communicate with our computer by entering text and viewing the output. A shell works like an interpreter. It understands the input we provide through our terminal and translates it into actions for our operating system. To execute tasks, our commands and applications need to utilize the hardware in our computer. This process is facilitated by the kernel. I hope this lesson was both fun and informative, and I can't wait to see you in the next one. Welcome to today's lesson. This lesson is all about creating directories within the terminal. We'll also delve into the Linux naming convention and learn how to use character escaping effectively. So, let's get started. Throughout your journey with Linux, one essential skill you'll need to master is creating directories. Keeping your files organized in several directories will help you locate and manage them with ease, as well as streamline your workflow. Thankfully, creating directories in Linux is as easy as pie. And who doesn't love pie? To demonstrate, let's create an images directory to store pictures of our cat. All we have to do is use the mkdir command, which is short for make directory, followed by the path we want our new directory to have. Since we want to create this new directory within our current location, which, as represented by the squiggly line, is our user's home directory, we can simply type the path to our current location, followed by a slash and the desired name for our new directory. In essence, this path represents the location our new directory would have if it already existed. While this command would work perfectly well, here's a little time-saving trick we can use. Instead of typing an absolute path every time we want to create a directory, we can use a relative path to save us from all that tedious typing. Need a refresher on relative paths? Since we're located in our user's home directory, we can subtract that part from our path, leaving us with just the name of our new directory. In practice, this means whenever we want to create files or directories in our current location, we only need to specify their names. Time to put it to the test. Let's use the ls command to check. Great! Our directory is alive and kicking. To further hammer this concept home, let's create a subdirectory within the images directory we just made. We'll name it cats and pretend it's for storing pictures of our adorable cat. Can you figure out the command we need to use to create this new directory? Remember, our objective is to create a directory called cats inside the images directory using a relative path. I'll give you 10 seconds. Ready, set, go! Figured it out? Here's the answer. To kick things off, we need to use the mkdir command. No surprises there. Then, we need to specify the path we want our new directory to have. To begin, we need to determine the relative path to the images directory, since that's where we want to create our new directory. Because the images directory is located in our current directory, its relative path is simply its name. Next, since we want to create our new directory within the images directory, we need to follow up with a slash and the name we want our new directory to have. And just like that, we're good to go. Now, let's double check our work. As we learned in a previous lesson, we can use the ls command to display the contents of a specific directory by entering its path as the argument. In our case, here's what that would look like. Let's put it to work. Success! Our directory was indeed created, and we don't even have to navigate there. Let's break out the catnip and celebrate. Now that we've mastered the art of creating directories, let's take a look at a few pitfalls to avoid when it comes to naming directories. Consider this command. At first glance, it looks like we're creating a directory called My Files, right? Well, let's give it a go and see what happens. No errors pop up, so we're off to a good start. Let's check if our directory was created using the ls command. Uh-oh. Instead of one directory, we ended up with two separate directories, one named My and the other Files. But why did this happen? It's because the terminal treats spaces as separators between multiple arguments. So, the mkdir command thought we wanted to create two different directories based on the two arguments we provided. That's why it's important that we follow a naming convention for files and directories. A naming convention is a set of guidelines that define how items within the command line should be named to prevent confusion and unexpected behaviors. In general, names within the command line should consist of letters, numbers, and the following special characters: periods, underscores, and dashes. Special characters are not interpreted by their literal values and may be misinterpreted, leading to unexpected results as we just experienced. For convenience, it's also recommended that we use lowercase characters exclusively and avoid excessively long file names, which can lead to finger fatigue. With these guidelines in mind, let's pick a better name for our directory. How about something like this? This name has got it all: lowercase letters, an underscore instead of a space, and isn't excessively long. Let's try it out. Time for the moment of truth. Let's verify with the ls command. Success! Our command was interpreted correctly and our directory was created. High fives all around! Even though it's strongly advised that we follow the naming convention when creating directories, sometimes we might need to bend the rules and use special characters or spaces anyway. We can do this with a nifty technique called character escaping. Escaping employs special characters to indicate that spaces or other special characters should be interpreted literally. For example, to escape a single character, we need to use a backslash before it. Here's what that would look like. The backslash tells the command prompt to treat the character that follows as part of the name of our new directory and not as a separator between two different arguments. An alternative to the backslash is using single or double quotes, which are especially useful for escaping multiple characters at once. Here's what that would look like. This way, both of the spaces in the name of our new directory are escaped at once. How cool is that? Keep in mind that we'll need to use these escaping characters every time we refer to this directory. For instance, here's what the absolute path for this directory would look like. Weird, right? That's why it's best to stick to the naming convention and save ourselves the hassle. Congratulations! You are now proficient in creating and naming directories. Let's recap what we've learned. To create directories, use the mkdir command, which stands for make directory, along with the path you'd like your new directory to have once it's created. You can use either an absolute or relative path for this purpose. When naming items in the command line, it's best to use letters, numbers, and the following special characters: periods, underscores, and dashes. Escaping is a technique that employs either a backslash or quotes to indicate that spaces or other special characters should be interpreted literally. Had a blast in this lesson, and I can't wait to see you at the next one. Welcome to another lesson. Today, we'll delve into the process of effortlessly creating and editing text files within the Linux command line. Let's dive right in. Last time, we conquered the art of creating directories. But what's a directory without some files to fill it? Throughout your journey with Linux, you'll frequently find yourself needing to create various types of files to store a wide range of data. To help you get started with this essential skill, let's begin by creating a simple text file. Unlike the mkdir command, which is specifically designed for creating directories, Linux doesn't have a dedicated command for creating files. But fear not, we have plenty of tricks up our sleeve to get the job done. When it comes to creating text files, one of the most popular methods involves using a text editor. As the name implies, text editors are specialized applications that enable us to create or edit text files. These humble yet powerful tools serve as the less glamorous alternatives to Microsoft Word found on Windows computers. Linux boasts a myriad of text editors, some of which you might have heard of, such as V or gedit. However, one text editor stands out from the rest: Nano. Regarded by many as the best text editor in the Linux world, Nano offers a user-friendly and intuitive interface that makes creating and editing text files a breeze. Now that we've hyped Nano up, let's learn how we can use it to create our very own text file. Doing so is very simple. All we have to do is type nano, followed by the path we would like our new file to have. Since we're creating this file in our current directory, its relative path will simply be the name we choose. Just like we learned in our previous lesson, make sure you always choose names that follow the naming convention. For this example, let's simply go with my_file. Optionally, we can also include an extension, not because it serves any specific function, but because it can make identifying that this is a text file easier. With our command ready, let's execute it. Welcome to the Nano text editor. It may look like any other text editor you've seen, but there's one key difference. We can't use a mouse to move the cursor around. Instead, we need to use the arrow keys on our keyboard. While it may feel a little clumsy at first, it works. Since we can't use a mouse, we rely on various keyboard shortcuts to perform different functions. For example, one of the most useful shortcuts is Ctrl and W, which searches for text within our file and is the equivalent to Ctrl and F on a Windows computer. Another handy shortcut is Ctrl, Shift, and minus, which transports us to a specific line in our file. This is useful when dealing with large files, because, as you can imagine, using the arrow keys can be slow and clumsy. Keep in mind, you don't have to memorize these shortcuts because they're conveniently displayed at the bottom bar within our editor. Here, you'll find all the shortcuts that can make editing files a breeze. In case you're wondering, the caret symbol, otherwise known as the tiny hat, represents the control key. But enough about shortcuts. Let's add a few lines of text. To exit and save our literary masterpiece, let's press Ctrl and X. Nano will then ask if we want to save our file. Since we do, let's press the Y key on our keyboard, which stands for yes. Next, Nano asks if we want to save our file under a new name. Since we want to keep our current name, let's press Enter. And we're done. To quickly view files within the terminal, we can use the cat command. Cat stands for concatenates. Yes, that's a real word. It means to merge things together, and it refers to the fact that this command can display more than one file at once. For now, we just need to view the contents of a single file, so let's type cat followed by the path to our file. Awesome! Our file was created and saved successfully. High fives all around. Apart from creating new files with the nano command, we can follow a similar procedure to edit an existing file. All we have to do is type its path after the nano command. The editor opens just like before, and from here, we can edit the file's contents to our heart's desire. Since we don't have any changes to make right now, let's simply exit the editor. Get cozy with the nano command, because we'll be using it quite a lot. Using a text editor is not the only way to create files within Linux. Although it's unlikely that you'll need to use these alternative methods often, we're including them here because you might come across them throughout your career or in examples online. First up is the touch command. Although this command is primarily used for changing the date and time at which a file was last modified, it can also be used to create files. Let's give it a try. All we have to do is type the touch command, followed by the path we'd like our new file to be. You can probably come up with some pretty creative names. But for this example, we'll simply use my heart. Let's try it. To confirm our file's creation, let's use the ls command. Great! Our file has materialized. From here, we can use a text editor to edit the contents of this file, just like we learned. Another way to create files in Linux you might encounter is by using the echo command. True to its name, echo simply repeats whatever we input as an argument, as demonstrated here. So, how can this be used to create a file? Well, we can direct the output of the echo command into a file using a technique called output redirection. Here's what that would look like. This approach channels the output of the echo command into a file of our choice. This comes in handy because it not only creates a new file, but also simultaneously adds some text to it. However, let's not get ahead of ourselves here. Output redirection is an advanced technique that we'll explore in detail in a future lesson. For now, just know that it's an exciting technique to look forward to. Give yourself a round of applause. You are now well-versed in creating files. Let's recap what we've learned on this lesson. Linux boasts a myriad of text editors. However, arguably the best is Nano. It offers a user-friendly and intuitive interface that makes creating and editing text files a breeze. Make sure you take advantage of the various keyboard shortcuts that the Nano command offers to make editing your files a whole lot easier. Other methods of creating text files that you might encounter involve using the touch command to create empty files and the echo command to create files with a few lines of text. I hope you've enjoyed this lesson, and I'll see you at the next one. Welcome to our next lesson. Today, we'll delve into the world of file management and learn how to perform various operations, such as moving and renaming files. Let's get started. As you navigate the world of Linux, you'll often find yourself needing to move files and directories from one place to another. Picture this. You might need to relocate a rarely used file into an archive directory. Or perhaps you accidentally created a file in the wrong location and need to correct it. Either way, knowing how to move files and folders around is essential. To help you get the hang of it, let's take a look at how we can move one of the files we created in our previous lesson. To do so, we need to use the mv command, which is an abbreviation for the word move. As the name implies, this command teleports files or directories from one location to another. To make it work its magic, we need to specify two paths. One is called the source, and the other the destination. The source is the path of the file we want to move, while the destination is the directory in which we want to move it into. Since both the file and the directory we want to move it into are located in our current location, their relative paths are simply their names. With our command ready, let's execute it. We don't see any errors immediately, which indicates that our command likely worked correctly. To confirm, let's use the ls command to check the contents of the My Files directory. Awesome! Our file has been successfully teleported. And here's the icing on the cake. The mv command works on both files and directories. This means that we could use it in exactly the same way to move entire directories along with their contents. Apart from moving files and directories, many times you'll be required to rename them as well. You might think that renaming is a piece of cake, but remember, there's no graphical interface here. We can't just right-click on a file to rename it. Instead, we need to use the mv command once again. That's right, there's no separate command for renaming. This is because the mv command doesn't actually move items around in the way you might imagine. Instead, it works by changing their paths. Since the name of an item is part of its path, By modifying the path, we can simultaneously change its name. In other words, because the name of an item designates its path, in the same way, its path designates its name. To grasp this sorcery, let's rename the images directory we created in a previous adventure. The first thing we need to do is type the mv command. Next, since the file we want to rename is located in our current directory, we can simply enter its name as our source path, just like before. For the destination path, we need to specify the path we want our directory to have once we rename it. Because the renamed directory will be located within our current location, its relative path will simply be its name. So all we have to do is specify the new name for our directory. With everything set, let's put our command to work. Now, let's use the ls command to see if our directory is sporting its new look. Success! Our directory has a brand new name. You might be scratching your head, wondering, how does the mv command know when to move an item and when to rename it? Is it magic? Telepathy? Nope. It's just cleverly designed. Here's the secret. If the destination path is an existing directory, mv moves the item into that directory, changing its path accordingly, just like our previous example. If the destination path doesn't exist, mv uses it as the new path for our item. Pretty cool, right? By knowing that mv works by changing paths, we can do some pretty cool stuff. For example, we can move and rename files at the same time. Let's try doing this on one of the files we created in our previous lesson. As always, let's start with the mv command followed by our source path, which is the path to our file, and the destination path, which is the path we want our file to have once it's moved and renamed. Since the destination we specified is not the path to an existing directory, the mv command will use this destination as the new path for our file, effectively moving and renaming it. Let's give it a try. Time for our trusty ls command to check the contents of the My Files directory. Drum roll, please. Success! Our file was both moved and renamed. How cool is that? You'll likely be using the mv command quite a lot, so get familiar with it. In summary, here's what we learned in this lesson. The mv command can be used to both move and rename files. It accepts two paths, one as the source and the other as the destination. The mv command checks whether the destination directory exists. If it does, it moves the item there. If it doesn't, it renames the item instead. Because the mv command works by changing an item's path, we can simultaneously move and rename items by specifying the path we want them to have as our destination. I hope you enjoyed this lesson, and I'll see you in the next one. Welcome to another lesson. Today, we'll continue our journey in the world of file management by learning how to copy and delete files and directories using the command line. Buckle up, and let's dive in. Within Linux, you'll often need to create copies of files and directories for various reasons, such as backing up important data or duplicating files before making modifications. After all, it's always good to have a plan B, am I right? Let's kick things off by making a backup copy of one of the files we created in our previous lessons. If you recall, we moved the files we created into the My Files directory, so let's use the ls command for a quick look inside. From the files that appear, suppose that we want to create a backup copy of the first file in the list. To do this, we need to use the cp command, which, fun fact, is an abbreviation of copy. Just like the mv command we looked at earlier, cp requires two paths, a source and a destination. For the source, we need to specify the path of the file we want to copy. First, Let's find the relative path to the My Files directory where our file resides. Since the My Files directory is in our current directory, its relative path is simply its name. Next, since the file we want to copy is nested within, we need to follow up with a slash and the name of our file. Next, for our destination, we need to specify the path we want our new copy to have. Let's place this new copy within our current directory. To do so, all we have to do is specify the name we want it to have. That's because, from our location, that would be its relative path. Think of it like this. If the copy already existed in our current directory, what would its relative path be? Well, just its name. With our command ready, let's give it a go. Everything seems to have gone smoothly. To confirm that our backup copy was created, let's use the ls command. Success! We now have a shiny new backup of our file. Give yourself a pat on the back and a celebratory high five. But don't go anywhere just yet, because it's time for some more action. The cp command can also be used to copy directories. Let's see what that looks like by creating a copy of our entire My Files directory and placing it in our current location. Just like before, we need to start with the cp command. For the source, since the directory we want to copy is in our current directory, its relative path is simply its name. For our destination, we can once again simply type the name we want our copy to have, because we want it to be placed within our current directory. Let's give it a try. Oops! It seems that the cp command refuses to copy directories unless the R option is specified. R stands for recursive and is a common option on many commands. In this case, cp requires it for copying directories because it needs to copy the items contained within them, and it won't do that unless we give it explicit permission. The R option gives it the green light. So, let's dust ourselves off and give it another go. This time, let's include the R option. Note that the cp command is strict about the order of options and arguments in this specific case. It requires that options are placed before arguments. With our command ready, let's give it another shot and hope for the best. Let's whip out the ls command to see what happened. Awesome! A brand new copy of the directory has appeared. What we can also see, however, is all the files and directories we've been creating throughout the last couple of lessons. We need to tidy up, because a clean workspace is a happy workspace. And what better time to learn how to delete files? To do this, we need to use the rm command, which is an abbreviation for the word remove. This command works on both files and directories, but just like the cp command, the R option is required when deleting directories. Since some of the items we want to delete are indeed directories, let's go ahead and specify the R option. Next to it, we need to type the paths to the items we want to delete. To delete multiple items at once, we can specify their paths as separate arguments. In the next lesson, we'll learn how to obliterate hundreds of files with just a few keystrokes. But for now, we're stuck typing away. With our command ready, let's hit go. It's time for our trusty ls command to check the aftermath. Our directory is now squeaky clean. Keep in mind, however, that deleting the wrong files could cause a lot of issues. So make sure you double check whatever you type whenever the rm command is involved. You're learning so much. Don't worry if it feels overwhelming. Using these commands will become second nature once you start working with the command line regularly. For now, just focus on getting a general idea of what they do. To recap today's lesson, use the cp command to copy files. It requires two paths, a source and a destination. The source is the path of the item we want to copy, and the destination is the path we want our copy to have once it's created. To delete files and directories, use the rm command. You can even remove multiple items at once by specifying all of their paths as separate arguments. When copying or deleting directories, the R option is required. This option allows our command to delete or copy the items contained within our directories. I hope you had a blast in this lesson, and I can't wait to see you at the next one. Welcome to today's lesson. Today, we're diving into the world of path expansion and wildcards, which are about to make your command line experience a breeze. Let's get started. Remember in the previous lesson when we had to manually type the path of every item we wanted to delete? Well, it's time to say goodbye to tedious manual labor, because we're about to learn how to select multiple files at once using just a single keystroke. First things first, let's create a series of files and folders to serve as our guinea pigs for this lesson. To create a few files, let's use the touch command. Now, let's whip up a couple of directories with the mkdir command. Let's use the ls command to make sure everything looks good. Awesome! Our test subjects are now ready. Now, imagine that we want to delete all the files and folders we just created. I know, it's like erasing a masterpiece, but hey, sacrifices must be made for the sake of knowledge. Let's begin with the rm command, followed by the R option. Next, to select all of our items at once, we need to use a technique called path expansion. Path expansion is a fancy name for a technique that allows us to use a special character to represent all the items in our current directory at once. These special characters are called wildcards, and the most popular of which is the mighty asterisk symbol. Here's how we can incorporate it into our command. The asterisk acts like a placeholder that represents any combination of characters. You can think of it as a one-size-fits-all solution for words. It allows us to select items with different names by automatically matching any sequence of characters that make up their names. When we execute this command, the shell recognizes the asterisk symbol and automatically replaces it with the names of all the items in the directory, effectively doing the tedious typing for us. How cool is that? It's important to remember that with great power comes great responsibility. This command would delete every item in our current directory without exception, so use it wisely. Let's hold off on executing this command. We need our test subjects intact for upcoming demonstrations. Alright, so now we've mastered the art of wiping out entire directories in one swoop. But what if we want to be a bit more selective? In that case, we've got you covered. Let's dive into some ways we can use wildcards to pick and choose our targets. For example, let's assume we want to delete all the files that end with a .txt extension. To do so, we can use the asterisk wildcard to represent any characters before our extension, followed by the extension itself. With this command, only the items whose paths end in .txt will be selected, regardless of what comes before that. Pretty nifty, right? But wait, there's more. Let's say we want to delete every item that starts with the word my. Can you guess what the argument for that would look like? I'll give you 10 seconds. Ready? Here's the answer. First, we must specify the word my, followed by the asterisk wildcard, which will represent every character that comes after. Piece of cake. Now, let's spice things up a bit. We can also use the asterisk wildcard to select files that contain a specific word or character within their names. For instance, let's say we want to delete all items that have an underscore somewhere in their names. To achieve this, we need to use a wildcard for every character before our target character, followed by the underscore itself, and then another wildcard for every character after that. Not only does this argument select all the items with an underscore in their names, but as a bonus, we've created an argument that looks like a face. In a similar way, you can use this wildcard to select a series of files based on any patterns you identify within their names. And remember, even though we're focusing on the rm command, path expansion works with any command within the terminal. It's like a universal remote. Apart from the asterisk symbol, we have several more wildcards to explore. While these remaining wildcards are used less frequently, chances are you'll still find them helpful. So, let's quickly go through them. First, let's examine the question mark wildcard. This wildcard is similar to the asterisk, but with one key difference. It represents a single character. In this case, the question mark wildcard represents any single character or number between the word file and the .txt extension. Pretty cool, right? Another wildcard we can use is a set of brackets. Like the question mark, this wildcard represents a single character. But instead of representing any character, it only represents the specific characters enclosed within the brackets. This allows us to be very specific about the characters we want to select. In this case, this argument will select items whose names start with the word file, followed by either the number 1 or 2, along with a .txt extension. Easy peasy. But wait, there's more. Instead of manually typing the characters we want this wildcard to represent, we can use various expressions. For example, we can specify a range by using a hyphen. Here's what that would look like. This wildcard will select every number from 0 to 9, while this one will select every character from A to Z. We can even get fancy by using expressions that represent different types of characters. For example, by using the following expression, we can select only uppercase characters. The colons surrounding the names of our expressions indicate to the shell that we're specifying an expression and not a series of characters. Now that we're done messing around with our test subjects, we can simply delete them. Wildcards are incredibly useful and can save you a lot of time, so be sure to take advantage of them. To recap what we learned, the asterisk wildcard represents any number of characters. It can be used to select items that start, end, or contain specific characters within their paths. The question mark wildcard works similarly to the asterisk, but with one key difference. It represents only a single character. The brackets wildcard allows us to specify which characters we want to select by enclosing them within the brackets. Various expressions can be used within the brackets to make this process easier. I hope you enjoyed this lesson, and I'll catch you in the next one. Welcome to another lesson. Today, we'll explore the various types of users that exist within Linux and learn how they differ from those in other operating systems. Let's jump right in. If you've ever used an operating system, you're likely familiar with the concept of users. Simply put, a user is an entity that utilizes a system's resources in one way or another. Simple enough, right? So why have we dedicated an entire lesson to them? Well, that's because users in Linux function slightly differently than they do in other operating systems. We'll learn more about that a bit later. First, let's take a look at the user accounts that exist within our computer. This information is stored in a file named passwd, within the /etc directory. Let's use the cat command to check it out. Why passwd, you ask? It's because this file, along with user information, is also used to store passwords. However, passwords have been moved to a separate, more secure location, which we'll explore in another lesson. In any case, let's take a look at it. Here it is. The format and structure of this file might seem a bit odd, but that's because the file is not necessarily made to be easily readable. Instead, it's made to meet the requirements of our operating system. Despite its unusual appearance, it'll work for our purposes just fine. Let's break down what we're looking at here. At the start of each line, we have the name of each user. You might be surprised to see so many accounts listed here. We'll learn what purpose they serve in just a bit. Following the name, the letter X is a placeholder for the user's password. As we mentioned earlier, passwords are now stored in a separate, more secure location. Directly after, we have the identification number for each user. These numbers are used internally to differentiate between users. Adjacent to that, we find the identification number for this user's group. Groups are simply collections of one or more users. Don't worry too much about this field for now. We'll delve deeper into groups in an upcoming lesson. Following that, we have a few brief comments that describe each user. In our case, the 3 commas each serve as placeholder characters in the place of a comment. The next field is probably the one you recognize. This specifies the home directory for each user. Finally, we have the path to the shell that gets initialized when each user logs in. In our case, it's a bash shell. Now that we've decoded the information within this file, let's dive into the different types of users within our computer. The first type of user we'll explore is the regular user, the bread and butter of Linux users. This is the type of user we've been using so far, and it's the one you'll spend the majority of your time working with on your computer. There can be multiple regular users, but in our case, we only have one. Regular users have limited access to certain files and directories, and they're restricted from performing certain actions. For instance, they can't access files that contain sensitive information, such as files that store user passwords, and aren't allowed to modify or delete files critical to the system's operation. These restrictions extend to the applications and commands they execute. That's because applications and commands inherit the same level of access as the user who initiated them. This means that since regular users can't access certain files, the applications or commands they execute won't be able to either. But why are regular users kept on such a short leash? Well, regular users are the ones who might accidentally delete important files, install malicious applications, and so on. Therefore, as you can imagine, giving this type of user a more limited scope of the system is generally a good idea. These restrictions also make it harder for attackers to access and compromise the system. For instance, if a regular user were to inadvertently execute a malicious application, these restrictions would make it much harder for this evil program to wreak havoc on our system. Additionally, these restrictions serve as a safety net against user mishaps. For example, imagine trying to delete the entire root directory while logged in as a regular user. No chuckles, this really happens. In such an event, the system would remain functional since regular users can't delete or modify essential files. However, all other files would be deleted. Yikes! While this is still a significant loss, it's far better than completely rendering the system inoperable. The second type of user is the root user, which is comparable to an administrator on a Windows computer. As the most powerful user on our computer, the root user can modify and delete any file and can execute any command without restrictions. But beware, with great power comes great responsibility. For example, if we were to delete our entire root directory while logged in as the root user, our operating system would undoubtedly become inoperable. Yikes indeed! This level of power might sound risky, but there's a method to the madness. You'll often need to log in as the root user to make changes to the system configuration files, install applications, or perform advanced operations. We'll explore this type of user in more detail in a future lesson. The third and final type of user is the service user. Unlike the previous two types, these users are not meant to be used by actual humans. Instead, they're created automatically and are meant to execute specific background applications. Take the syslog user, for instance. This user operates an application that stores and manages messages generated by the kernel or various programs. These messages provide valuable information about system activity and performance. Service users, such as the syslog user over here, are not meant to log into the system at all. In fact, many of these users have /non-existent specified as their home directory, indicating that they don't have a valid home directory. Instead of a shell, the application initialized when service users log in is usually no login. This is a program that, upon login, displays an error message and terminates the login session immediately. It's like a self-destruct sequence, preventing further interaction with the system. Now, you might be scratching your head wondering, why have users that aren't meant to log in at all? That's because service users are used as mechanisms that isolate applications and files from the rest of the operating system. Specifically, service users are the only ones that can view or modify the files that make up the applications they execute. This ensures that the sensitive data contained within them remains protected and is inaccessible to every other user. Why is this necessary? Imagine that an attacker infiltrated our system through an infected application installed by a regular user. Surprise, surprise! Since our service user is the only one that can access the files that make up the applications they execute, this attacker, who would inherit the same level of access as our regular user, wouldn't be able to access their contents. Pretty cool, right? If the concept of non-human users still sounds like something out of a sci-fi movie to you, don't worry. In the upcoming lessons, we'll dive deeper into how users within Linux function, and you'll be able to better understand them. So stay tuned. For now, here's a quick recap. Regular users have limited access to certain files and directories, and are restricted from executing specific commands. These restrictions help secure the system and safeguard against potential user mishaps. The root user is the most powerful user account on our computer, with access to everything within the computer. This user can modify and delete any file and can execute any command without restrictions. Service users are created automatically and are meant to execute certain background applications. They're permitted to use only the files they need to function, which ensures the stability and security of our system. Thank you for joining us on this expedition into the world of Linux users. Until our next lesson. Welcome everyone. Today, we'll dive into the world of file permissions and ownership. We'll explore what these concepts are and how they maintain the security and integrity of our system. Let's dive in. As we learned in our previous lesson, different types of users have different levels of access to the files within our operating system. Now, you might be wondering, what's stopping them from accessing files and directories they shouldn't be able to? This is where file permissions come into play. These are attributes that define who can view, modify, or interact with a specific file or directory. With file permissions, our system can expertly control who can do what with each file. Let's kick things off by examining the different types of file permissions. The first of which is the so-called read permission. As you might have guessed, this attribute allows users to view or read the contents of a file. Remember when we used the cat command to peek into various files? We were only able to do that because the user account we were using was granted the read permission for those specific files. Next up is the write permission. This attribute grants users the ability to modify a file, such as altering its contents, moving, renaming, or even deleting it. Essentially, the write permission provides users with the ability to make changes to the file as they see fit. Last but not least, we have the execute permission. This permission behaves differently depending on whether it's applied to a file or directory. When it comes to files, the execute permission is only applicable to executable files, such as those that reside within the /bin directory. These are special types of files that can be run as programs, similar to .exe files on a Windows system. By granting this permission, users are allowed to run these files as programs. We'll learn more about executable files in a following lesson. For directories, the term execute takes on a different meaning. Assigning the execute permission to a directory allows users to access its contents and navigate within it. This means they can use the ls command to look at the files inside and the cd command to navigate within. Now that we've learned about the different types of permissions, you might be wondering, how are these permissions assigned? This is where the concept of ownership comes into play. In Linux, every file and directory is assigned a user owner. To demonstrate, let's create a new file with the touch command and see which user account is assigned ownership. To view the owner and the assigned permissions to this file, we need to use the ls command coupled with the L option, which stands for list. This option presents the output of the ls command in a convenient list format that reveals information about the file's permissions and ownership. Let's try it. Here it is. We'll decode each field soon, but for now, let's zoom in on the third field. This column displays the name of the user account that's designated as the owner of this file. Generally, the user who created the file is assigned ownership, which is why we see our username listed here. But wait, there's more. In addition to a user owner, files and directories are also assigned a group owner. A group is essentially a collection of users. The name of the group that owns this file is specified adjacent to the user owner. In this case, this group is named after our username. However, let's not get ahead of ourselves. We'll learn all about groups in a subsequent lesson. All you need to know for now is that groups represent a collection of users. Now that we've unraveled the mysteries of user and group ownership, let's see how all this ties into file permissions. Both user and group owners are assigned permissions for the files they own, which are indicated in the first column. While it may seem like a cryptic enigma at first glance, this column consists of a series of characters that represent the permissions granted to each owner. This series of characters is divided into 4 sections. Let's go through them. The first section consists of a single character that denotes the type of file we're dealing with. A dash represents a file, while the letter D signifies a directory. In our case, we see a dash, which means we're looking at a file. Next, we have a trio of characters that represent the permissions granted to the user who owns the file. Letters signify specific permissions, while dashes take the place of missing permissions. The letter R stands for read permission, W for write permission, and X for execute permission. In our case, the user owner has read and write permissions, but not the execute permission. Since this file isn't executable, this permission is irrelevant in this case. Since we're logged in as the user who owns this file, these permissions indicate that we're allowed to view and modify this file. Generally, the user owner has the most control over the file, meaning they're granted more permissions than other owners. The third section is another set of 3 characters, this time revealing the permissions for the group that owns the file. In our case, every member of the owning group has the read permission for this file, but lacks other permissions. Finally, the last set of 3 characters denotes the permissions for every user who is neither the owner nor a member of the owning group. In our case, this category of users only has read permissions for this file. Generally, this category of users is granted the least control over files, mainly for security reasons. Allowing broad access to a file would make it easier for an attacker to infiltrate and access it. To illustrate, suppose that an attacker infiltrated an application run by a service user. As we learned in our previous lesson, the applications that a user executes inherit the same level of access as the user who executed them. So, this attacker would have the same level of access as the service user. This service user is not the user owner for this file, because that would be us. And let's assume they're not a member of the owning group. This means that this hypothetical service user would only be able to interact with this file according to the permissions assigned to the others category of owners. As a result, the attacker would be able to read the contents of this file, but not be able to modify or execute it. Phew! Crisis averted. Before we wrap up, let's satisfy your curiosity about the remaining fields, shall we? The second column displays the number of shortcuts that exist to this file. The fifth column indicates the file size in bytes. Next to that, we have the date and time at which the file was last modified. And finally, the last column contains the name of each file, though you probably could have figured that out on your own. Go ahead, give yourself a round of applause. You've now mastered the essentials of file ownership and permissions, and you're ready to conquer the upcoming lessons. Let's take a quick trip down memory lane and revisit the key takeaways. File permissions are specific attributes that dictate who can read, write, or execute a particular file. Our system uses these file permissions to selectively restrict the ways files can be accessed and by which users. File permissions are assigned to entities that share ownership of the file, which are referred to as owners. These owners consist of a user and a group of users. These permissions apply not only to users, but also to the applications they execute. When users execute applications, these applications inherit the same level of access as the user who initiated them. I hope you found this lesson engaging and informative. Stay tuned for more lessons as we continue to explore the world of file permissions, ownership, and groups. See you in the next one. Welcome to another lesson. Today, we'll explore the root user. We'll learn what its purpose is and how we can use it effectively. So strap in your digital seatbelts and let's get started. From our previous lessons, one type of user that likely made an impression on you is the root user. Also called the super user, this user is created automatically, and there can only be one root user in our computer. It's considered the most powerful user because it's not subject to file permissions. That's right, the root user can read, write, and execute any file, regardless of who the file's owner is or what permissions have been assigned. Consequently, the root user can execute any command and perform any modifications to the system. At this point, you might be wondering, why is a root user even necessary? Why can't our regular user have the same privileges? In Linux, different users have different roles and responsibilities, and are assigned permissions based on these roles. Regular users, for instance, are meant to handle day-to-day activities like creating files, downloading items, or running simple applications. On the other hand, logging in as root is typically necessary for completing advanced tasks, such as modifying configuration files or performing significant system-wide alterations like installing applications. By segregating the responsibilities of each user and limiting their access accordingly, we can prevent accidental or intentional damage to the system, which can occur if a user has excessive privileges. For example, if our regular user has the same privileges as our root user, they could accidentally delete crucial system files and cause irreparable damage. This clever distribution of duties helps ensure the security and stability of our system, while also allowing us to perform advanced operations when needed. So, when would we ever need to log in as the root user? As we mentioned earlier, the root user can perform operations that regular users cannot. To illustrate how the root user comes in handy, let's walk through a task that can only be performed with root privileges. Remember in a previous lesson where we went through the contents of the passwd file? In that lesson, we briefly mentioned that user passwords are now stored in a different, more secure location. Specifically, passwords are now stored in a file named shadow within the /etc directory. Due to the sensitive nature of this file, only root can access its contents. To illustrate, let's use the ls command along with the L option to take a peek at the /etc directory. Great! The owners and the permissions for every file in this directory have been displayed. The keen-eyed among you may have noticed that every file in this directory is owned by root. But why is this the case? This is a security measure that prevents unauthorized access or the modification of these crucial system files. If these files were owned by a regular user, they would have the ability to modify or delete these files, potentially causing problems. By having root-owned system files and assigning the necessary permissions, we can ensure that these files are not accidentally or intentionally modified by regular users or the applications they execute. Take a look at the shadow file in particular. You'll notice that only root and members of the owning group have the read permission for this file. Our regular user is represented by the others category, which doesn't have the read permission for this file. But hey, let's give it a shot for giggles. Let's try viewing the contents of this file using the cat command. An error pops up telling us we don't have the necessary permissions. No surprise here. So, should we just log in as root to view this file? Hold your horses. While we could, we've preached the importance of limiting our level of access to the system at all times so that we can maintain the security of our system, as well as safeguard against potential mishaps. If only there was a command that allowed us to execute commands as if we were root, but only temporarily. Well, you're in luck. Allow me to introduce you to the sudo command, which stands for super user do. If you've used Linux for any length of time, you've likely come across this command. As the name suggests, it allows us to execute commands as if we are the root user, but only for a single command. It may sound complicated, but it's actually quite simple. Here's how it works. Sudo accepts only one argument, the command we want to execute as the root user. Let's type sudo, followed by the cat command, and the location of the file we want to view. It's important to note that not all users have the ability to execute the sudo command due to security reasons. However, a regular user does, so let's give it a try. Before you can enjoy your newfound power, you'll need to input your password for security reasons. Success! While it may resemble an extraterrestrial language, the sequence of letters and symbols is actually the encrypted password for each user. In programming, it's considered good practice to never store passwords in plain readable text. So, this cryptic format keeps our passwords safe from prying eyes. You might have noticed that most users don't have passwords. What's up with that? Well, those are service users, and since logging into them is not possible, a password is not necessary. But what about the root user? Why doesn't it have a password either? That's because, to log in as root, we can use the sudo command instead of supplying a password. As we mentioned before, the sudo command allows us to execute commands as if we're the root user. Because we're executing commands with the highest privileges possible, we can just make ourselves the root user with no questions asked. So, the root user having a password would be redundant. Let's see what this looks like in action by logging in as root. We'll use the su command, which stands for switch user. As the name implies, it allows us to change our current user. To use it, type sudo followed by the su command, along with the name of the user we want to switch to. In this case, that would be root. Success! We're now logged in as the root user. As we explained before, the sudo command granted us the necessary permissions to log in as the root user without requiring an additional password. But remember, with great power comes great responsibility. So be careful with every command you execute. A single misstep could make your entire system go haywire. That's why using the sudo command is considered good practice, and logging in as root should only be done when absolutely necessary. To tie things up neatly, let's switch back to our regular user. There's no need for the sudo command while logged in as root, so to switch back, simply type su, followed by the username of your regular user. And there you have it! You now know what the root user is and how to use it effectively. Throughout your journey with Linux, you'll be using the sudo command quite frequently, so be sure to familiarize yourself with it. Let's recap. The root user allows us to perform advanced operations on our computer without any restrictions. It's created automatically, and there can only be one root user on our computer. Sudo stands for super user do, and as the name suggests, it can be used to execute a single command as if we are the root user. To change the user you're currently logged in as, use the su command, which stands for switch user, along with the username of the user you want to switch to. Thanks for joining us in this lesson. We'll see you in the next one, where more Linux adventures await. Welcome to another lesson. Today, we're going to dive deep into the concept of groups, learn how they function, and explore how they allow users and applications to access files securely. Let's get started. In a previous lesson, we learned that file permissions are assigned to multiple owners, including a group of users. But what exactly are groups, and why do they exist? Simply put, we can use groups to allow a specific set of users to access a file. To better understand this concept, let's take a sneak peek at the various groups that exist on our computer. The file containing this information is appropriately named group, and it resides within the /etc directory. As always, let's use the cat command to check it out. Now, let's break down what we're looking at here. The first column displays the name of each group on our computer. Some of those might ring a bell. We can spot a group named after our regular user, as well as other groups like syslog or root. But why are these groups named after usernames? That's because when a user is created, a corresponding group is automatically created and associated with that user. In other words, every user on our computer has its own group. It's like an exclusive fan club for that user. Groups associated with a user are called primary groups, and they always contain at least one user, the user with whom they're associated with. This means that, unlike you in high school, every user is part of a group. Groups not associated with any users are called secondary groups. For instance, the sudo and shadow groups we see here aren't named after any corresponding users, making them secondary groups. Unlike primary groups, secondary groups are not created automatically and are not associated with any users. Beside each group's name, the X symbol is a placeholder for each group's password. That's right, Just like users, groups can be secured with a password. However, group passwords aren't commonly used, so let's just pretend this column is invisible. Just like you felt during that awkward phase in middle school. Moving on, the following column displays the identification number of each group. These numbers are used internally to differentiate between groups. Finally, in the last column, we have the members of each group. You might be wondering why some primary groups appear to have no users listed. That's because it's always assumed that the user they're associated with is a member of the group, which is why their usernames aren't displayed here. Now that we understand what we're looking at, let's learn a bit more about groups. As we mentioned earlier, groups enable us to selectively allow access to files and directories for many users at once. To illustrate, remember the mysterious shadow file we examined in our last lesson? That file is owned by the shadow group, which we can see here. This group is assigned the read permission for the shadow file, which means that every member of the group is allowed to read its contents. In this case, the group is empty, but if we added ourselves to the shadow group, we'd be able to view the contents of the shadow file with our regular user account, without needing the sudo command. However, that would be a huge security risk, so let's not actually do that. The key takeaway here is that the permissions assigned to the group owner of a file apply to all the members of that group. This mechanism allows us to securely allow access to a file for a select number of users. But what's the point of an empty group? While no user is a member of this group, many applications are. To better understand this, let's take a look at the permissions of the shadow file. As always, let's use our trusty ls command. As you can see, this file is owned by the shadow group, which is assigned the read permission for this file. This means that every member of this group has the ability to read the contents of this file. Apart from users, however, files and applications can also be members of groups. Specifically, every file that's owned by this group can be considered a member. In other words, the shadow file can be considered a member of the shadow group. In the same way, any other files or applications owned by the shadow group would also be considered its members. Like we said before, every member of this group is permitted to read the contents of this file, no matter if they're a user or an application. This is precisely why this group exists in the first place. It simply enables several applications to read the contents of this file. This ensures that these interactions take place securely and exclusively between the relevant parties. How cool is that? Without groups, the only alternative would be to assign the read permission to the others category of owners. That would be like giving away the keys to the kingdom, because everyone represented by that category would be allowed to access the sensitive data within this file. This includes service users, regular users, and every application they execute. Talk about a security nightmare. As a result, using groups is the most effective way to selectively and securely allow access to files, whether that's for users or applications. And there you have it. You now have a solid understanding of what groups are and how you can use them. In the next few lessons, we'll be putting all this theory into practice by securing an application of our own. So stay tuned. For now, let's recap what we learned in this lesson. Every time a user is created, a primary group is also created and associated with that user. Groups not associated with any users are called secondary groups. Groups can be allowed a specific set of users to securely access a file. The permissions assigned to the group owner of a file determine the permissions for every member of that group. Groups can also be used to enable applications to securely access files. Whenever two files are owned by the same group, they can interact with each other according to the permissions assigned to their group owners. I hope you enjoyed this lesson, and I'll catch you in the next one. Welcome, fellow security enthusiasts! In this lesson, we'll learn how to secure files and applications by creating dedicated user accounts and modifying file ownership. Let's jump right in. Over the past few lessons, we've been uncovering the mysteries of ownership and permissions. In this lesson, we're going to tie all that knowledge together and learn how to secure files and applications by creating dedicated user accounts. In general, applications that handle sensitive data or need to access important system files or resources should be owned and executed by a dedicated user. You might be thinking, hold up, this sounds a lot like service users, which we discussed in a previous lesson. Although the purposes of service users and dedicated users may seem identical, there is a key distinction between the two. Service users are designed to isolate and secure applications related to our system's operation, while dedicated users aim to isolate and secure applications of our choice. Web and database servers are prime examples of applications typically run with dedicated users. Web servers host websites, while databases store various types of sensitive data, such as usernames and passwords. Since these applications handle sensitive data and often need to access critical system files, it's considered good practice to have them owned and executed by a dedicated user account. It's like hiring a digital bodyguard. Why go to all this trouble, you ask? By creating a dedicated user and assigning it as the owner of every file that makes up an application, we can modify their permissions to ensure that only our dedicated user can interact with them, effectively excluding everyone else. In other words, this is what the file permissions for these files would look like. These permissions dictate that only the user owner, in this case our dedicated user, is allowed to interact with our application. All other users, or the applications they execute, won't be able to engage with our application, whether their intentions are good, bad, or simply clumsy. It's like building a digital fortress for our application. This protection goes both ways. As long as we don't assign any permissions to the others category of owners for any files in our system, we can guarantee that our dedicated user won't be able to interact with them. Why is this useful? Picture a scenario where an application executed by a dedicated user experiences a catastrophic bug that causes it to delete every file on our computer. Since the dedicated user for this application lacks the necessary permissions to interact with any other files, and because applications inherit the same level of access as the user who executed them, every other file would remain untouched. Now that's a pretty cool safety measure, right? However, it's important to remember that not every application needs its own dedicated user account. That's because this level of security is a bit excessive. Generally, most applications can be owned and executed by our regular user. Nonetheless, as we mentioned earlier, creating a dedicated user is a good idea when it comes to certain applications. Now that we know why dedicated users are awesome, let's roll up our sleeves and secure an application of our own. Since we haven't learned how to install applications just yet, let's create a file using the touch command and use our imagination to assume it's a very important application we need to secure. Now that our application has been created, it's time for us to put on our security hats and get to work. First, let's use the ls command along with the L option to check what permissions our precious file currently has. As we mentioned before, when a user creates a file, they're automatically assigned user ownership, and their primary group is assigned group ownership. However, our goal is to secure and isolate this file by creating a dedicated user and group, and assigning it user and group ownership instead. To conjure up a new user, we need to use the user add command, which does exactly what its name suggests. Following that, we need to specify the name we want for our new user to have. It's essential to note that, by default, the user add command creates users that aren't meant to be logged in. Why, you ask? Well, without specifying any options, this command creates users without a home directory or a password, which is exactly what we want in this case. Remember, we only need this new user to assign it ownership of our application. We don't need to log into it. So let's give it a shot. Oops, it looks like we missed. What gives? It seems that we don't have the necessary permissions to execute this command. The shell tells us that it cannot lock the passwd file. But what does that mean? Lock in this context refers to accessing a specific file. As you can imagine, the user add command needs to modify the contents of the passwd file to create our new user. However, our regular user doesn't have write permission for this file, so it's unable to do so. The simple solution is to use the sudo command, which temporarily turns us into the almighty root user. As we mentioned in our previous lesson, root users aren't bothered by those pesky permissions. So, let's dust ourselves off and give it another try. Success! Our new user is alive and kicking. As we mentioned earlier, whenever a user is created, a primary group with the same name is automatically created as well. So, we can cross creating a group off our to-do list. What we do have to worry about is making our application accessible only by the dedicated user we created and no one else. To pull this off, we need to use the chown command, which is short for change owner. This command can be used to change both the user and the group owner of a file in one fell swoop. To do so, we need root privileges. So let's start by typing sudo, followed by the chown command, the username we want to assign user ownership to, directly followed by a colon, and the name of the group we'd like to assign group ownership to. In this case, that would be our user's primary group. Finally, we need to specify the path to our application. With our command ready, let's hit go. No errors? That's a good sign. Let's use the ls command to double check. Success! Both the user and the group owner of this file have now been changed. All that's left to do is modify the permissions of this file so that only our dedicated user can interact with it. But let's not get ahead of ourselves here. We'll learn all about that in our next lesson. For now, let's take a moment to recap what we learned. Applications that handle sensitive data or require access to important system files or resources should be owned and executed by a dedicated user. By creating a dedicated user and assigning it as the owner of every file and directory that our application needs, we can protect and isolate it. The user add command can be used to create users, and the chown command is useful for changing both the user and the group owner of a file. I hope you had a blast during this lesson, and I can't wait to see you on the next one. Until then, happy securing. Welcome back, everyone. In today's lesson, we're going to learn how to modify file permissions so that our files and applications are secure and accessible only by the appropriate users. Let's dive right in. In our previous lesson, we learned that the first step in isolating and securing an application involves creating a dedicated user account and assigning it ownership of every file that comprises our application. For our imaginary application, the next step is to modify its permissions so that only the user owner can interact with it. To begin, let's examine the current permissions of our file using the ls command. As you can see, our user owner is assigned the read and write permissions for this file. Since we're assuming this is an application, we must also assign the execute permission to the user owner. Additionally, we need to isolate our application and make it inaccessible to every other user. Currently, members of the owning group and all other users have the read permission, which we must revoke. Ultimately, the file permissions should appear as follows once we're finished. With our eyes on the prize, let's master the art of changing file permissions. We'll use a command called chmod, which stands for change mode, as in mode of access. This command can be employed in two ways: symbolic mode and octal mode. We'll start with symbolic mode, which uses symbols or letters to represent the permissions we want to modify. To demonstrate how it works, let's assign the execute permission to the user owner of the file. Modifying a file's permissions demands the power of a superuser. So let's begin with the sudo command, followed by chmod. We then need to type the letter that represents the owner whose permissions we want to change. The letter U denotes the user owner, G represents the group owner, and O stands for others. In our case, we need to change permissions for the user owner, so let's type the letter U. Next, we need to type either a plus or a minus sign, depending on whether we want to add or remove a permission. Since we want to add a permission, let's type the plus sign. Now, we need to type the letter that represents the permission we want to add. We want to assign the execute permission, which, as we learned in a previous lesson, is represented by the letter X. Finally, we need to specify the path to our file. With our command complete, let's hit that Enter key. No errors appear, which is always a good sign. To verify, let's use the ls command. Success! The execute permission has indeed been assigned to the user owner. Now that we've assigned the execute permission, it's time to remove the permissions for the group owner and others, just like a bouncer at an exclusive digital club. The chmod command allows us to change permissions for multiple types of owners simultaneously. Once again, let's start by typing sudo along with the chmod command. Just like before, we need to type the letters that represent our owners. The group owner is represented by the letter G, and others are represented by the letter O. Since we want to remove a permission, let's follow up with the minus symbol. Next, let's type the letter that represents the permission we want to remove, which in this case is the letter R, followed by the path to our file. Looks like we've done it again. Let's verify with the trusty ls command. Awesome! The permissions have been modified as intended, and our application is now accessible only by the user owner. But wait, there's more. We've got more chmod tricks up our sleeve. Even though our application is now secure, let's explore a few more ways we can use the chmod command. For instance, here's how we can change multiple permissions at once. Can you decipher what this command does? I'll give you 10 seconds to crack the code. Ready? Here's the answer. This command assigns every permission to every owner. The permissions would appear as follows. Pretty cool, right? In addition to the plus or minus signs, another symbol we can use within the chmod command is the equal sign. The equal sign adds a specific permission while removing all others. For example, this command would assign the read permission to every owner and remove all other permissions. In other words, the permissions would appear as follows. Pretty simple, right? So far, we've only explored the chmod command in symbolic mode. Now, let's uncover the secrets of octal mode. Although we generally recommend using symbolic mode, let's learn octal mode just in case you ever come across it. Let's start with a simple example. In octal mode, permissions are specified as a 3-digit number, where each digit represents the permissions for the user, group, and others, respectively. Each permission is represented by a digit, where 0 represents no permissions, 1, the execute permission, 2, the write permission, and 4, the read permission. By adding up these numbers, we can assign multiple permissions at once. In this example, all owners would be assigned the read, write, and execute permissions because the numbers 4, 2, and 1 add up to 7. I double-checked with a calculator. If we had the number 6 instead of 7, it would represent the read and write permissions because only the numbers 4 and 2 can add up to 6. It requires a bit of math, but once you get the hang of it, octal mode can be rather straightforward. Another example is the enigmatic number 5, which can only be comprised of the numbers 4 and 1 from our options, representing the read and execute permissions, respectively. Catching on yet? Now, a test of your mathematical prowess. What would this command do? Remember, 0 represents no permissions, 1 represents the execute permission, 2 represents the write permission, and 4 represents the read permission. You have 10 seconds. Time's up. The answer? This command would assign the write permission to the user owner. Hopefully, you figured out that much. The owning group would receive the write and execute permissions because only the numbers 2 and 1 can add up to 3. Lastly, everyone else would have read and execute permissions because only the numbers 4 and 1 can add up to 5. In summary, stick with symbolic mode. And there you have it. You now know all about the chmod command, and you can use it effectively to modify file permissions. Let's recap what we learned in this lesson. Chmod stands for change mode and can be used to change the permissions of a file. It can be used in 2 ways, symbolic and octal mode. In symbolic mode, letters represent owners, followed by symbols, such as a plus or minus sign, along with 1 or more letters representing permissions. In octal mode, permissions are specified as a 3-digit number, with each digit representing the permissions for each owner, respectively. I hope you enjoyed this lesson, and I can't wait to see you at the next one. Welcome to another adventure in the world of computer security. Today, we're diving into the concept of groups and how they can be used to securely grant access to files. Let's begin. In our previous lessons, we delved into securing files by restricting access to a single user. However, there are plenty of scenarios where you might need to grant access to a select group of users or applications without sacrificing security. This is where groups come to the rescue. To achieve this, we can simply create a new group, assign it ownership of our target file, and then make the necessary users or applications members of that group. The permissions we set for the group owner will then apply to every member of that group. For instance, if we assign the read permission to the group owner of our file, every member of that group will be allowed to read its contents. By doing this, we can effectively allow a specific set of users or applications to access our file. How cool is that? At this point, you might be wondering, why not just modify file permissions directly to achieve the same effect? While that's technically possible, it isn't the most secure or efficient method. To illustrate, let's whip out the ls command to to take a look at our file's current permissions. As you can see, only the user owner can access this file at the moment. To grant access to another user, we'd have to adjust the permissions for the others category of owners. Doing this, however, would open up access to every user and application on our system, rather than just the specific set of users and applications we want to allow access for. It's like hosting a party and accidentally inviting the entire town. Talk about a security nightmare. A more secure option would be to limit access to only those who require it. You might be thinking, why not just add the necessary users as members of the user owner's primary group? While this could work, it would also grant them access to every other file owned by that same group, provided the permissions allow it. We could, of course, lock down the permissions for every other file in that specific group, but a more elegant solution is to create a separate, dedicated group. This new group will be the proud owner of just the files we want to share, and its members will be our hand-picked users or applications. By doing this, we can ensure that only the selected users have access to the designated files, without compromising the security of other files. It's like forming a secret club where only the cool kids are allowed. Alright, it's time to roll up our sleeves and put all this theory into practice. Let's create our first group and make it the proud owner of our file. To create this group, we need to use the appropriately named group add command. Let's start by typing sudo, followed by the group add command itself, and the name we want our new group to have. To verify that our group was created, let's check the contents of the group file. Awesome! Our group has successfully entered the digital world. Now that our group is ready, let's make it the owner of our file. This time, we can't use the chown command like we did in a previous lesson, because while chown can change group ownership, it can only do so while also changing user ownership. It's like a 2-for-1 deal. To change only the group owner, we need to use the chgrp command, which stands for change group. Once again, let's start with the sudo command, followed by the chgrp command, the name of our group, and the path to our file. Time for the trusty ls command to check our work. Success! The group owner of this file has been successfully changed. Hold up though, we can see that the group owner isn't assigned any permissions yet. That means that members of this group won't be able to access this file. To make our file accessible to the members of this group, we need to use the chmod command, just like we learned in the previous lesson. Try to figure out the command we need to use. Remember, our goal is to assign the read permission to the group owner. Ready, set, think! And here's the answer. The letter G stands for group. The plus sign adds a permission, and the letter R represents the read permission. An alternative would be the equal sign, which adds a permission while removing all others. Either option would work like a charm in this case. Let's give it a go. Now, let's double check with the ls command. Fantastic! Every member of this group can now read the contents of this file. Time to celebrate with a virtual high five. Now, it's time to assemble our group members. Since we don't have any actual users that need access, we'll use our regular user as a test subject. The command we need to use is called usermod, which is short for user modification. As the name suggests, This command can be used to make various changes to a user's properties, such as their username or password, as well as adding or removing them from a specific group. To do so, let's type sudo, followed by the user mod command itself. Then, we need to use the A option. A stands for append. Without this option, the user mod command would remove us from every other group we're members of before adding us to this one. Next, we'll use the G option. G stands for group and instructs the user mod command to make a specific user a member of a group. Note that the G must be uppercase, as lowercase g constitutes a different option entirely within the user mod command. Finally, let's type the name of the group, followed by the name of our user. Drum roll, please. Let's execute our command. To verify that our command worked, let's check the contents of the group file, just like before. Success! As you can see, our user is now a member of the group we created. Let's see if we can now read the contents of our file. Wait, what? No permissions? It's because whenever we make changes related to the user we're currently using, we need to log out and log back in for the changes to take effect. So, let's use the logout command to do just that. Now, let's log back in. Let's try viewing the contents of our file once again and see if this fixed our issue. Fingers crossed. Success! No errors this time, which means we nailed it. If you're wondering why there's no output, it's because our file is empty. There's simply nothing to display. Give yourself a pat on the back. Just like we gave a user access to this file, we can do the same for an application. All we need to do is make the group we created the owner of every application that needs access to this file. It's like giving them a VIP pass. As we mentioned in a previous lesson, we can think of files owned by a group as members of that group, just like users are. So, whenever two files share the same group owner, they're allowed to interact with each other, assuming their permissions allow them to do so, of course. Before we sign off, let's clean up our workspace. Let's start by using the groupdel command to delete the group we created. Next, let's use the userdel command to delete the user we created. And finally, let's use the rm command to delete our file. That's a wrap, folks. You now know how to securely allow a set of users or applications to access a file. Here's a quick recap of what we learned in this lesson. We can make files accessible to a select number of users and applications by creating a group and assigning it ownership of our file. Every member of that group would then be allowed to access our file securely. Whenever you need to change the group owner of a file without changing user ownership as well, use the chgrp command. Use the usermod command along with the G and A options to add users to groups. Make sure you log out and log back in if your changes are related to the user you're currently using. I hope you had a blast during this lesson, and I'm looking forward to our next adventure. See you soon! Welcome to this lesson. Today, we'll delve into the world of application packages and learn how we can use them to install applications. Let's get started. Linux, like any other operating system, supports the installation of a wide variety of applications, ranging from humble text editors to mighty enterprise-grade web servers and databases. These applications are distributed in the form of packages. Think of packages as neatly wrapped boxes that contain all the files that an application needs to function, such as executables, documentation, and any other resources. For all you Windows aficionados out there, packages are similar to files with a .msi extension, or installers as they're also known. Now, let's roll up our sleeves and get hands-on with a package of our own. We've whipped up a simple application package as our guinea pig for this experiment. First, let's download our package from GitHub using the wget command, which is short for webget. True to its name, this command allows us to download files from a given link. To use it, all we have to do is type the wget command, followed by the URL of our package. We've included this link in the description of this lesson so that you can effortlessly copy and paste it into your terminal. Awesome! Our package has been downloaded. Let's use the ls command to make sure it's really there. Fantastic! There's our package. It contains a very simple application that, when executed, prints "Hello World" into our terminal. We'll see what that looks like in just a bit. You may be curious about the .deb extension at the end of our package. Packages come in a variety of formats, depending on the specific distribution they're meant to be installed on. Deb signifies Debian, one of the most beloved Linux distributions. Since we're using Ubuntu, which is largely based on Debian, it's no surprise that it accepts the same types of packages. Time to install it. Installing applications calls for root privileges, so let's kick things off with the sudo command. Afterwards, we need to use the dpkg command, which is short for Debian package. To instruct it to install our package, we need to use the I command, which stands for install, along with the path to our package. Let's try it. Awesome! Our application has been installed successfully. Let's take it for a spin by typing its name into our terminal. Success! Our application is alive and kicking, and you've just leveled up in the world of Linux. For the inquisitive minds among us, you might be itching to know, what exactly did the dpkg command do? As we hinted earlier, packages contain executable files and other resources necessary for an application to function. Essentially, installing a package refers to placing those files into the appropriate directories. For instance, executable files are placed in several directories designated for storing executable files, such as /usr/bin. Let's use the ls command to take a peek inside. Aha! The output reveals the executable of our newly installed application, sitting pretty among its peers. But what makes this directory so special? To grasp this, we must first delve into the inner workings of commands and applications in Linux. At the heart of every command and application lies a single executable file, as we can see here. When we type a command or an application's name into our terminal, we're essentially instructing the system to run a corresponding executable file. The underlying mechanism that makes this all possible is quite simple and elegant. The moment we enter the name of our application into the terminal, the shell searches for a corresponding file within several designated directories. Once it finds the matching file, it executes it, much like double-clicking a .exe file in a Windows system. This ingenious process lets us execute commands and applications without needing to memorize their precise paths every time we want to use them. Instead, we simply type their names into our terminal, and the shell will take care of locating and executing the corresponding file. How cool is that? Apart from the aforementioned directory, the shell looks for executables in other directories as well, such as /sbin, which stands for system binaries. This directory contains executable files for commands that perform more advanced tasks, such as user add, user del, and group add. Besides executable files, applications are made of several other types of files as well. These files are also neatly organized into designated directories. Not because they serve a specific function there, but simply to ensure that they're well organized. Let's take a guided tour of some of these directories, starting with the /usr/lib. This directory stores something called application libraries, which are collections of code utilized by multiple applications. They're the Linux equivalent of .dll files in a Windows system. Another such directory is the /usr/share. This directory stores data files, documentation, and other non-executable files used by applications. There are other directories of a similar nature, but these two are the main attractions. It's important to note that we don't expect you to memorize all this information. The key takeaway is that installing an application refers to placing all of its files into their designated directories, either because they serve a specific purpose there, or to maintain that beautiful, organized structure we all love. Another burning question you might be itching to ask is, how on earth does the dpkg command know where to place every file that makes up an application? Is it telepathy? Magic? Or is it just a stroke of genius? To uncover some clues, we must investigate the package itself. To do so, we need to use the dpkg-deb command, which is designed for creating, managing, and uninstalling packages. To reveal the contents of our package, we need to use the C option, which stands for contents, followed by the path to our package. Like we said before, packages are like boxes that contain all the files that make up an application. What we see here is every item within this package. First, we spot the root directory of the package, followed by a directory named /usr, and nestled within that, a subdirectory named bin. Does this ring a bell? Inside the subdirectory, we discover the executable for our application. This is not a coincidence. The structure and position of each file within this package determine where the file will be placed within our system. That's precisely how the dpkg command knows where to place files. It simply examines their location within the package and places them in corresponding directories within our system. Pretty cool, right? This means that if you ever want to know what changes a package will make to your system, all you need to do is examine its contents. This knowledge is sure to come in handy. Now, let's tidy up before we close the curtains. Let's go ahead and uninstall our Hello World application by using the dpkg command, along with the R option, which stands for remove. We'll also bid farewell to the package we downloaded using the rm command. Give yourself a round of applause. You've gained a solid understanding of packages and their inner workings in Linux. To recap, here's what we learned. Applications are distributed as packages, which are collections of files that make up a program. Packages include executable files, documentation, and any other resources needed for the software to run. Installing packages involves placing their files into the appropriate directories, a process facilitated by the dpkg command. Typing a command into the terminal instructs the shell to execute a file with the corresponding name. The shell searches for executables in several directories, such as /usr/bin. I hope you enjoyed this lesson as much as I have. Go forth and conquer the world of Linux with your newfound expertise. See you in the next lesson. Welcome to another exciting lesson. Today, we're going to learn what package managers are and understand how they make the process of installing applications more efficient and user-friendly. Let's dive in. In our previous lesson, we learned how to install applications by downloading and installing packages. However, instead of all that tedious manual labor, we can employ something called a package manager. These incredible applications automate the process of installing, updating, and removing software, making our lives a whole lot easier. Think of package managers like the App Store on your phone. They contain a vast number of packages, allowing us to install them quickly and easily. What's so utterly fantastic about package managers, you ask? For starters, they make installing new applications as easy as pie. Just tell your package manager which app you want and watch as it takes care of the whole process for you. It's like having a personal butler for your software. But wait, there's more. Package managers also handle something called dependencies. Dependencies are any supporting software that's required for an application to function. For instance, remember the /usr/lib directory we explored in our previous lesson? Our package manager ensures that we have all the essential libraries in this directory, so that our software can function properly. And, as the cherry on top, package managers can also be used to keep our software fresh and updated. Say goodbye to scouring the web for updates. Of course, no tool is perfect. One of the few drawbacks that package managers have is that within their collection, they might not have that one obscure app you want to install. For lesser-known applications, you might have to resort to manually downloading and installing their packages. But hey, we can't have it all, right? Despite this limitation, package managers are an invaluable tool that we'll be utilizing throughout this course. Now, let's have some fun and install our first app using a package manager. We'll be installing Cowsay, a quirky little program that displays messages through an art cow. You'll understand when you see it. It might not be the most practical app, but it's a fantastic way to learn the ropes. So, let's go ahead and use a package manager to install this application. Different Linux distributions come with different package managers. Debian-based distributions, such as Ubuntu, include a package manager named apt, which stands for Advanced Packaging Tool. This package manager provides a variety of commands for different operations. The most important of which is apt-get, which can be used to perform basic package management tasks such as installation, update, and removal of packages. Let's try it. To install packages, we need super user privileges. So, let's start by typing the sudo command. Afterwards, let's use the apt-get command, followed by the install option. You might notice that this option is not preceded by a hyphen like options typically are. It's not strictly necessary for options to be preceded by hyphens. Instead, it's up to the developer to dictate the syntax of a command. With that said, to complete our command, the last thing we need to do is type the name of the package we want to install. Hold on to your keyboards, folks, because we're about to break down the magical process that happens when you install an app using a package manager. The apt-get command starts by reading something called the package lists. These lists contain information about every package that can be installed on our system, including details about where to download packages from and what dependencies they require. We'll learn more about package lists in upcoming lessons. Next, we've got the building dependency tree stage. which refers to using the information from the package lists to figure out which dependencies need to be installed alongside this specific application. Reading state information refers to the apt-get command figuring out which packages are already installed on our system, which packages are currently being used, and which packages have been marked for installation, upgrade, or removal. This ensures that we don't install a package that's already on our system or one that conflicts with another. apt-get then plays matchmaker, suggesting a related package it thinks you might like. It's like a software dating service. It then tells us which packages will be installed, including any necessary dependencies. In this case, Cowsay is a simple application that doesn't require any additional software to function. It then proceeds to download the appropriate packages using the information from our package lists. Afterwards, it unpacks the downloaded files. To save on space and bandwidth, packages come in a compressed format, similar to a .rar file on a Windows computer. Unpacking refers to extracting the package from the compressed archive. Setting up our package refers to installing the package. In other words, placing the files within it in the appropriate locations, just like we learned in our previous lesson. Finally, we have processing triggers, which is like the cherry on top, completing miscellaneous tasks like updating configuration files or creating directories. In this specific case, the apt-get command ensures that there is an entry in the manual pages for the application we just installed. And there you have it, folks. With one simple command, our app is installed and ready to go. How amazing is that? Is your head spinning from all that info? We understand that this information is quite in-depth, and we don't expect you to remember every single action that occurs during an application's installation. Instead, we aim to provide you with a general overview of the installation process, so you can understand the impact of installing an application, determine what will be installed, and troubleshoot any issues that might arise during the process. Now that we've learned how to install applications, it's time to play with our new app. Let's just type the Cowsay command, followed by a few words. Isn't it utterly fantastic? What's the purpose of this app? Well, it's just a lighthearted way to display messages on the command line. Sometimes, you just gotta have a little fun. To wrap up, you now know what package managers are and how to use them to install apps. Here's a quick recap. A package manager is an application that automates the process of installing, configuring, updating, and removing applications. The apt-get command can be used to perform basic package management tasks such as installing, updating, and removing packages. Package lists contain information about every package that can be installed on our specific distribution, including details about where packages can be downloaded from and their dependencies. I hope you had a blast during this lesson, and I'll see you in the next one. Happy package managing! Welcome to another lesson. Today, we're going to explore the concept of repositories and learn how our package manager utilizes them effectively. Buckle up and let's dive in. In our previous lesson, we learned that package managers need a wealth of information to function effectively, such as which packages are available, where they can be downloaded from, and what dependencies they require. Enter package repositories, the grand online libraries that contain all the packages that can be installed on our system, along with a wealth of information about them. Wait a minute, this sounds familiar. It sounds a lot like package lists, which we touched upon in our previous lesson. That's no coincidence. Package lists are essentially offline copies of repositories. But let's not get ahead of ourselves. We'll get into all of that in the next lesson. For now, let's focus on repositories. Our package manager's primary source of packages is the official repository provided by the developers of our distribution. Let's hop onto our web browser and check it out. The official repository for Ubuntu can be found at the following link. Here we are! But before we start exploring, keep in mind that repositories are designed to be accessed by package managers. As a result, their structure is not exactly intuitive for human readers. As such, we won't be diving into every single directory in great detail. Instead, our goal is to give you a solid grasp of what repositories are and what information they contain. So, let's break down what we're looking at here. All the items listed here are directories that contain all sorts of information. The one that holds all the juicy package info is named /dist, which stands for distributions. This directory contains packages for various versions of our Linux distribution. Let's click and explore. Here's the lowdown on what we're looking at. Every version of Ubuntu is assigned a unique code name. For instance, version 22 of Ubuntu is codenamed Jammy. This repository contains several directories for each version of Ubuntu, which, in turn, store different types of packages. The packages these directories contain vary based on their development stage and the extent of testing they've undergone. Testing, in the context of software applications, refers to the evaluation of their functionality, performance, and security. This process is typically carried out by the developers of our distribution or quality assurance teams responsible for ensuring that packages meet certain quality standards and function as intended. The directory named after our codename contains the main packages for that specific release. These packages have undergone extensive testing and are considered stable. As a result, they're less likely to cause issues during installation or updates. When updated versions of packages become available, they're placed in the Updates directory. These updates could bring bug fixes, fancy new features, or performance improvements. Although they've been tested, they haven't been scrutinized as much as the packages in the main release. Some of these packages may eventually be incorporated into the main release once they've been deemed stable enough through additional testing. New versions of packages that fix security vulnerabilities are added to the Security directory. These packages have been tested to ensure they address the specific issues they're intended to fix, but may not have undergone the same level of testing as the packages in the main release. The Proposed directory offers early access to packages with new features, bug fixes, and improvements. Lastly, the Backports directory contains packages taken from newer versions of Ubuntu and modified to work with our specific version. These packages may offer new features and improvements, but might not have undergone the same level of testing and validation as packages in the main release. You might be scratching your head wondering, why are there so many different directories instead of just one that stores all these packages? Categorizing packages in such a manner allows users to choose between packages that have the latest features versus the packages that are most stable. That's right. We can decide which directories our package manager installs packages from based on our preferences. Users eager to use the latest features and willing to take the risk of upgrading to newer versions can opt for packages from the Proposed and Backports directories. Conversely, users who prioritize system stability and want to avoid potential issues can stick to packages in the main release. In an upcoming lesson, we'll learn how we can select which directories our package manager downloads packages from according to our needs. So stay tuned. Let's venture further into the main release and see what treasures await us. Here, packages are further categorized into 4 subdirectories, depending on whether they're available for free or whether they're maintained by the official developers or the community. Here's a quick rundown. The main directory contains free packages maintained by the developers of our distribution. Restricted refers to packages that are maintained by the official developers but are not free. Packages in the Universe directory are free and maintained by community members. Lastly, packages in the Multiverse directory are not free and are maintained by community members. Don't worry about memorizing all of this. We just want you to grasp the general distinctions between these directories in case it comes in handy. Let's step into the main directory. Here, we can see several more directories, each containing packages designed for different types of hardware. For example, if you're using a 64-bit computer, which you likely are, the directory, which contains packages compatible with your system, should have the term AMD64 somewhere within its name. Found it! Time for a closer inspection. Notice the 2 files named packages. Both of these files contain the same information, but are compressed in different formats. These are similar to .rar and .zip files on a Windows system. To access the information inside, we'll need to unpack one of them. Let's go with the .xz file. To download it, let's first copy its link. Then, let's head back to our terminal and use the wget command with the copied link. As always, let's verify with the ls command. Here it is! With our file downloaded, let's extract its contents. To unpack files compressed in the .xz format, we need to use the unxz command, which stands for unpackxz, along with the path to the file we just downloaded. Once again, let's use the ls command to verify. Success! Our compressed file has been transformed into a regular text file. Let's take a peek inside using the cat command. Feast your eyes on a wealth of information about all the downloadable packages, including names, versions, dependencies, and download locations. This is the exact information that the apt-get command uses to install packages. How cool is that? And that's a wrap for today. Before we say our goodbyes, let's quickly recap what we learned in this lesson. Package repositories store all the packages that can be downloaded for a specific distribution, along with various information about them. Repositories have several directories for each version of our distribution. These are categorized based on their development stage and testing status. Packages are further categorized into 4 subdirectories based on whether they're available for free and whether they're maintained by the official developers or the community. I hope you enjoyed this lesson about package repositories. Stay tuned for more lessons, and I'll see you in the next one. Welcome to our next lesson. Today, we'll delve into the world of package lists and discover how they can help us keep our applications up to date. Get ready to supercharge your package management skills. As we learned in a previous lesson, package managers heavily rely on information from repositories. The trouble is, several issues arise when it comes to accessing a remote repository. For one, retrieving the necessary information can be time-consuming and inefficient due to the sheer volume of data involved. Additionally, if a repository becomes temporarily unavailable, perhaps due to high traffic or a software bug, we won't be able to install new packages or update our current ones. This can be critical when dealing with time-sensitive security updates, for instance. Worry not! Our package manager has a clever trick up its sleeve. Say hello to package lists. We've teased them before, and now it's time for us to see them in action. Package lists are local copies of our repositories that allow our package manager to retrieve the information it needs quickly and efficiently. Storing this data locally offers several significant advantages. For one, it allows for nearly instantaneous access, compared to the time-consuming process of retrieving data from a remote repository. Additionally, local copies enhance reliability. If our repository goes down or experiences high traffic, we can continue working as if nothing happened. That's all to say that local copies allow our package manager to obtain the information it needs far more quickly and reliably. Now that we've hyped up package lists, let's get cozy with them. Let's navigate to the directory in which they reside. The /var directory, which stands for variable, contains files that are generated by the system or its applications during operation. They're called variable files because their content and size can change over time as the system or applications make modifications to them. Our package lists are stored in several subdirectories within it. Let's teleport there. From here, let's use our trusty ls command to see what we're working with. Here they are. Each one of these files contains information that was retrieved from different sections of our repository. Take this file for instance, which contains the packages from the main release. Let's take a look at it. Does this look familiar? It should. Remember when we downloaded our repository's contents in a previous lesson? Well, that's pretty much what this file is. In essence, package lists are local copies of our repositories, meaning the file we downloaded earlier and the one we're examining now contain the exact same information. Our package manager simply fetches this file from our repository and stores it in this directory for easy access. But there's a catch. Maintaining local copies of repositories presents a challenge. The information within them changes constantly. New updated packages may be released, or entirely new packages may be added. Consequently, our package lists can quickly become outdated, leading to issues such as our package manager being unaware of new security updates, or new versions with bug fixes and other fancy improvements. That's why we need an efficient method for keeping our package lists updated. So, how do we keep our package lists in tip-top shape? Manually downloading data from our repository and placing it in this directory is an option, but it would involve navigating the repository, downloading and unpacking archives, and transferring their data into this directory, and then repeating this process for every subdirectory our repository contains. All of which sounds incredibly time-consuming, doesn't it? Thankfully, there's a much better way. Our package manager offers a simple command that automates this process, fetching information from our repositories and updating our package lists accordingly. Say goodbye to tedious manual labor. Let's give it a shot. Simply type sudo, followed by the apt-get command, along with the update option. Awesome! The apt-get command iterates through all the different directories within our repository and updates our package lists accordingly. Our package lists are now up to date, and all it took was a single command. Talk about a time saver. As we mentioned earlier, updating our package lists is essential for ensuring that we're aware of updated versions of our applications when they become available. After all, nobody wants to be stuck with outdated software, right? Keeping our applications up to date is crucial for maintaining the security and stability of our system. Software updates often include fixes for security vulnerabilities, helping to protect our system from potential security threats and attacks. Additionally, these updates often come with bug fixes and performance improvements, enhancing the stability and reliability of our software. In other words, keeping our software up to date is a must. Lucky for us, our package manager has got us covered once again. It provides us with a simple command that updates all of our applications at once. Let's try it. All we have to do is type sudo, followed by the apt-get command, along with the upgrade option. This command checks our package lists and determines which of our applications can be upgraded. Specifically, it looks at the currently installed versions of our applications and compares them to what's available within our package lists. Let's give it a try. Here we can see a list of applications that can be upgraded. We're then asked to confirm that we want to go forward with the upgrades. So let's simply press the Y key on our keyboard to confirm. Y obviously stands for yes. The operation may take a few minutes to complete, depending on the number of applications that need to be upgraded. So go ahead and grab your favorite snack in the meantime. And there you have it! All of our applications have been successfully upgraded and are ready for action. As we've emphasized throughout this lesson, it's essential to keep both your package lists and your applications updated to maintain the optimal performance, security, and stability of your system. So make sure you execute both of these commands periodically. Give yourself a pat on the back. You've now mastered the art of updating package lists and applications. In this lesson, we've covered several key points. Package managers often require information from repositories. To streamline this process, they store local copies of our repositories, known as package lists. Because information within repositories constantly changes, our package lists quickly become outdated. To keep them current, use the apt-get command along with the update option. Maintaining up-to-date applications is vital for the security and stability of your system. To update your applications to their latest versions, use the upgrade option with the apt-get command. I hope you had a blast learning with me. I can't wait to see you in our next lesson. Welcome to another lesson. Today, we're going to learn how to manage our repositories and even add some of our own. Let's get started. Repositories, as you may recall, are neatly organized into various sections, each containing different types of packages. These packages vary based on their development stage and the level of testing they have undergone. This organized structure allows us to choose the packages that best suit our system's requirements. If you're all about security and stability, for instance, you might opt for packages from the main release, which undergo rigorous testing while steering clear of others. To dictate from which sections our package manager selects packages from, we can simply edit the contents of the sources.list file located in the /etc/apt directory. Let's whip out the cat command for a closer look. Let's decipher what we're looking at here. The first word before each link specifies the package format used by the repository. Deb refers to Debian packages, which means that the repository contains packages in the .deb format. You may also come across deb.src, which represents a repository with source code. Source code consists of files that need to be compiled or assembled to create the final package. It's perfect for when you want to tweak an application's code. Think of it as a DIY kit for software. Right next to that, we've got the links to the repositories themselves. The following field should ring a bell. It specifies the directory within the repository from which our package manager installs packages from. As we noted earlier, packages from the main release undergo the most thorough testing and are considered the most stable. Packages from the updates and security sections may not be as rigorously tested, but are still considered stable enough for use in production environments. By default, our package manager installs packages from the main release, updates, backports, and security sections. If you need to change from which sections your package manager installs packages from, you can add or remove entries as needed. However, proceed with caution. It's generally advised not to mess with this file unless you have a specific reason to do so. After all, if it ain't broke, don't fix it. Finally, the last field is another one you might recognize. This specifies the subdirectory within our repository from which our package manager installs packages from. Just to refresh your memory, the main and restricted subdirectories contain officially supported, stable, and secure packages. In contrast, the universe and multiverse subdirectories contain packages that are not officially supported by Ubuntu and may be less stable or secure. By default, entries for all subdirectories are included. For instance, the main and restricted subdirectories from the main release are specified here, while the universe and multiverse subdirectories have separate entries, which we can see here. To enable or disable any of these subdirectories, simply add or remove entries as needed. The keen-eyed among you might have noticed that packages from the security directory are downloaded from a different repository. This separate repository holds the same packages as the main repository. However, by downloading security updates from a distinct source, we can ensure that we'll still be able to install security updates, which are vital for the security of our system, in the event that the main repository experiences issues or becomes unavailable. Redundancy is key. In addition to managing existing repositories, there are situations in which you might need to add a repository of your own. For example, you might want to install a lesser-known application that's not available in the official repository. Fear not! We've whipped up a custom repository just for you, featuring the Hello World application we installed during a previous lesson. Are you ready to welcome this shiny new repository to your collection? Let's do it! You might be itching to edit the sources.list file and add an entry there. But hold on. When it comes to adding third-party or non-official repositories, it's generally recommended that we follow a slightly different methodology. Allow me to introduce you to the sources.list.d directory. Let's start by navigating there. This directory is specifically designed to store files that contain entries to third-party repositories. Our package manager will scan the contents of every file in this directory looking for entries. This allows us to create a new text file and type out our entry within it. By adding repositories here, instead of editing the sources.list file directly, we can manage our repositories in a more organized and modular way, with each file containing the entries for a specific repository. We'll see what that looks like in just a bit. But first, let's take a peek at this directory using the ls command. As the output reveals, the directory is currently empty, which means we aren't using any third-party repositories at the moment. Let's change that by welcoming our first third-party repository. Instead of painstakingly creating a file and adding an entry with the nano command, we can use the add apt repository command to automate this process. This command streamlines the process of adding a repository by automatically creating a new file that contains the link to our repository and placing it within this directory. To add our repository, we need superuser privileges. So let's start by typing sudo, followed by the add apt repository command, and the link to our repository. You might notice that this link looks a bit unusual. That's because we're using a PPA, or Personal Package Archive repository, which is one of the most common ways developers make their packages available. A PPA is a type of repository that contains packages from a specific developer. The first part points to the developer, while the second highlights the application. The PPA prefix gets translated by the add apt repository command into the appropriate URL, and an entry gets created accordingly. Let's see what that looks like by running this command. To confirm we want to add this new repository, let's simply press Enter. As you can see, this command not only adds our new repository, but also updates our package lists accordingly. In some older versions, this might not be the case. If the add apt repository command doesn't update your package lists, you can always run the apt get update command manually. In any case, let's use the ls command once more to double check that a file was created. There it is! It appears our repository was added successfully. Let's satisfy our curiosity by using the cat command to peek inside this file. Great! Our new file was created, and it contains an entry to our new repository. As you can imagine, having a dedicated file for each repository makes managing all the entries within it much easier. With our shiny new repository in place, it's time to install our new application. Let's use the apt-get command, followed by the install option, just like we learned previously. And just like that, our app has been installed and is ready for action. To use it, we can just enter its name in the command line. Awesome! Thanks to third-party repositories, you can now explore the world of lesser-known packages with ease, adding a valuable skill to your system management toolkit. Since our little experiment is over, let's clean up by uninstalling the application and removing the repository we just added. First, we'll say goodbye to our app by using the apt-get command along with the auto-remove option. Next, let's remove the repository we added by using the add apt repository command along with the remove option. This command essentially just deletes the file that was created. Give yourself a round of applause! You've conquered the art of managing repositories and installing apps from third-party sources. We learned that we can dictate from which section of our repository our package manager installs packages from by editing the contents of the sources.list file. Our package manager reads the contents of every file within the sources.list.d directory and searches for entries. By using this directory, we can manage our repositories in a much more organized and modular way. We can add new repositories by using the add apt repository command. This command adds repositories simply by creating new files within the sources.list.d directory. Thanks for joining us on this lesson. I hope you had as much fun as I did. Catch you in the next one. Welcome back, everyone. In this lesson, we'll learn how to create and execute our very own executable files. Let's jump right in. Picture yourself working in a Linux system, typing away commands for various tasks like copying files, installing apps, or creating users. It can get tedious, right? That's where scripts come to the rescue. A script is essentially a text file that contains a series of commands. Creating and executing these scripts allows us to automate repetitive tasks swiftly and efficiently. For instance, we can create scripts that automatically update our applications, or scripts that notify us whenever an application misbehaves or needs our attention. To better understand how scripts work, let's start by creating our first script. Remember the Hello World application we've been using throughout the last couple of lessons? Let's learn how to create just that. As we touched upon earlier, scripts are text files that contain a sequence of commands. So, to create our first script, let's use the nano command. From here, we're ready to write our new script. Scripts can be written in many programming languages, but for our purposes, we'll be creating a shell script. This means that we'll be creating a script that contains a series of commands that will be executed one after the other by our shell, hence the name. Before we get our hands dirty with code, it's necessary that we specify which program should be used to interpret the contents of our script. For example, if we were creating a Python script, we would need to tell our shell to use Python to interpret the contents of our script. In our case, we'll be creating a shell script, which needs to be interpreted by the shell itself. To do this, we'll be using something called a hashbang or a shebang line. A hashbang is simply a special comment that's placed at the beginning of our script and specifies the interpreter that should be used to execute our script. For our purposes, to indicate that this file contains shell commands and is intended to be interpreted by a shell, we need to type the hash symbol, along with an exclamation mark, followed by the location of our shell. If we were creating a different type of script, such as a Python script, we would replace the location of our shell with the location of our Python executable. With the interpreter sorted, it's time to write the code that brings our script to life. We're creating a simple Hello World application, so our script just needs to print Hello World in the terminal. To achieve this, we'll use the echo command, which is a handy utility that prints the text we input as an argument. It's like the print or console.log function in other programming languages. So, to make the echo command proudly proclaim Hello World, we need to type echo followed by Hello World. What's more, we can include comments within our script to provide context or explain the code. Comments are denoted by a hash symbol at the beginning of a line. The shell will then ignore everything on that line, allowing us to include any notes or explanations without affecting the execution of our script. In our case, we'll be using comments throughout the following lessons to explain every line of code we type. Great job! You have successfully created your very first shell script. Now, let's save our masterpiece and exit our editor. To do so, let's simply press the Ctrl and X keys on our keyboard. Nano will then prompt us to confirm if we want to save our changes. Let's press the Y key to confirm. Afterwards, let's hit Enter to confirm the name of our file. With our script ready, let's execute it. Before we can do so, however, we need to complete a crucial step: granting the necessary permissions. Let's begin by using the ls command to inspect our file's current permissions. As you can see, files created with Nano are not executable by default. To change this, we need to use the mighty chmod command to assign the execute permission, just like we learned in a previous lesson. With our permissions in place, we're ready to unleash our new script. You might assume that simply typing the name of our script into our terminal would suffice. However, doing so would prompt our shell to search for a corresponding file in the directories where it typically looks for executables, such as /bin or /usr/bin. To get around this, we need to specify the path to our script, rather than just its name. This tells the shell exactly where the file we want to execute is located, so it doesn't have to search for it in the usual directories. As a nifty shortcut, we can use a dot, followed by a slash, and the name of our file. A single dot represents our current directory. So, this syntax is the equivalent of typing our current directory followed by the name of our script. Let's try it. Success! Our script was executed flawlessly. If you wanted to execute this script without specifying its path each time, you'd have to relocate it to one of the directories in which the shell seeks out executables. However, since this script isn't particularly useful or frequently executed, there's no need to do that. And there you have it! You now have a solid understanding of what scripts are and how to use them. Here's a quick recap of what we covered in this lesson. Scripting is a powerful technique for automating various tasks within a Linux system. A shell script is essentially a text file that contains a series of commands that are executed by the shell. A hashbang, or a shebang line, specifies how the contents of a file should be interpreted. It specifies which application should be used to understand and execute the contents of our file. To execute a script, type its path into the terminal instead of its name directly. This tells the shell where the file is located so that it doesn't have to search for it in the usual directories. I hope you enjoyed this lesson, and I'll see you in the next one. Keep exploring and expanding your scripting skills. Welcome to this lesson. Today, we're going to explore variables and arrays. We'll learn how they work and understand their significance in making our scripts more dynamic and efficient. Let's get started. Variables are the building blocks of scripting. They serve as crucial components in storing and manipulating data within our scripts. Think of them as versatile containers capable of holding various types of data, such as text, numbers, or even paths. To better grasp this concept, let's go through the process of creating a variable step by step. First, let's revisit the script we created in our previous lesson. From here, let's remove the echo command and type the code that will make up our new and improved script. Creating a variable is a breeze. All we have to do is type the name we want our new variable to have, followed by an equal sign, and the data we want it to store. The equal sign is what we call an assignment operator, and as you can imagine, it simply instructs our shell to assign a specific value to our variable. This could be a number or a series of characters. Keep in mind that variable values containing spaces or special characters must be enclosed in quotes, just like arguments with spaces. This ensures that the spaces, or special characters, are treated as literal characters, rather than being interpreted in some other way by the shell. Now that we've conjured up a variable and filled it with data, let's use the echo command to reveal its value. Let's start by typing echo, followed by a $sign, and the name of our variable. The $sign tells the shell to substitute the name of our variable with its stored value. Without it, the echo command would print the variable's name instead of its value. With our script complete, it's time for the exciting part, executing it to see if it works. Let's first save and exit the editor. Now, let's execute our script just like we learned in our previous lesson. We don't need to worry about pesky permissions this time, because we already took care of that in our previous lesson. Fantastic! Our new variable was created successfully. and its value was revealed using the echo command. Now that we've mastered the basics of variables, let's dive even deeper and explore some interesting ways we can use them. Apart from characters or numbers, variables can hold a wide range of data types. Let's modify our script once again to showcase this versatility. An exciting feature of variables is their ability to capture the output of a command using a clever technique called command substitution. To demonstrate, let's use the date command to capture the current date and time and store it as the value of our variable. To do so, we need to type a $, followed by the command that is to be executed within parentheses. This syntax instructs the shell to use our command's output as the value of our variable. Without the $ and the parentheses, the word date would be assigned as the value, rather than the output of the date command. Yikes! Let's give it a spin. You know the drill by now. First, we need to save and exit the editor. And from here, let's execute our script. Awesome! Our variable captured the current date and time, and the echo command displayed it successfully. Impressive, right? But wait, there's more. What if we want to store more than one value within a single variable? No worries, we've got you covered. Variables that store multiple values are called arrays, and if you've programmed before, you've likely encountered them. Let's create an array of our own by editing our script once again. Creating an array is easy as pie. All we have to do is enclose the values in parentheses and separate each value with a space. Remember, if the values themselves contain spaces, wrap them in quotes. With our array set up, let's use the echo command to display its values. To do this, we need to follow a specific syntax. First, we need to enclose the array's name in curly brackets. The curly brackets signal to the shell that the specified variable is an array. Next, we need to select a value within the array by using square brackets. Inside them, we need to type a number that corresponds to the position of the desired value within the array. 0 refers to the first value, 1 to the second, and so on. In this example, the echo command will display the first, second, and third values in our array. Let's put it to the test. Save and exit the script. And then let's execute it. Excellent! Our array was created successfully, and its values were displayed as intended. At this point, you might be wondering, what are the real-world applications of these concepts? Let's dive into a practical example that'll make your inner geek dance with joy. Picture this. You need to create a simple script that generates a backup copy of a specific file. As always, let's kick things off by editing our script with the nano command. From here, we don't need all this code, so let's delete it. Now, we need to use the cp command to create our backup. To do this, let's type cp followed by the source and the destination file paths. For this example, let's make a backup of the passwd file. Next, let's have the echo command notify our users that the backup is complete. At this point, our script is functional, but it has some limitations. It can only create a backup of a single predefined file. To back up a different file, we would need to manually modify the source and destination paths in both the cp and echo commands. This might seem trivial for a few changes, but imagine the inconvenience of updating tens or even hundreds of occurrences. Here's where variables come to the rescue. Let's create two variables to store our paths, one for the source and one for the destination. Now, let's use these variables within our commands. This way, if we want to create a backup of a different file, we only need to change the values of these two variables instead of making numerous changes throughout the script. How cool is that? But why stop there? Let's take it a step further by allowing users to input the desired source and destination paths themselves. This way, we eliminate the need for modifications to the script altogether. Here's where the read command comes in. This command prompts our users to enter a value and then stores that value in a new variable. To use it, let's start by typing the read command, followed by the P option and the message we want to display to our users. Finally, let's type the name we want our new variable to have once it's created. Let's repeat this process for our second variable. Our script is now ready, so let's save and exit. Drum roll, please. It's time to run our script. As you can see, we're prompted to enter a value for our first variable, so let's type the path of the file we want to back up. Now, let's repeat this process for the destination path. It seems like our script worked, but let's use the ls command to verify. Success! A backup of the file we specified has indeed been created. Thanks to variables and the read command, we can create backups for any file without touching the code. How cool is that? Throughout the next few lessons, we'll be using variables and arrays extensively to create all sorts of scripts, so stay tuned. For now, here's a quick recap. Variables allow us to store data within a script, acting as containers for values like text, numbers, or file paths. Variables can also store more than one value. These are called arrays. By using command substitution, we can use the output of a command as the value for a variable, allowing us to easily retrieve and manipulate data from various sources. The read command can be used to prompt users to provide a value for a variable. This allows us to use the same script for different tasks without any modifications to its code. I hope this lesson sparked your curiosity in the power of shell scripting. See you in the next one. Welcome to another lesson. Today, we'll dive into the world of conditional statements. We'll learn what they are and how we can use them effectively. Let's dive right in. Conditional statements are the key to enabling our scripts to make decisions based on specific conditions. They allow us to control when to execute a set of commands and when not to, thereby adding a layer of intelligence to our scripts. To better understand this concept, we'll break down the structure of a basic conditional statement. At the heart of a conditional statement is the if keyword, which specifies the command that is to be evaluated. The shell then executes the specified command and checks whether its execution was successful or not. A command's execution is considered successful when it completes its intended task. If the command encounters an error and fails, its execution is considered unsuccessful. Depending on the result of the evaluation, the shell will either execute the commands following the then keyword or do nothing in the event that an error occurred. Lastly, the fi keyword is used to mark the end of our statement. Easy peasy, right? But wait, there's more. Conditional statements can also incorporate several other keywords. Let's check them out. Starting with elif, which is short for else if. This keyword allows for the evaluation of additional comments. In this example, our shell will start by evaluating the command next to our if keyword. If this command is executed successfully, the shell will then execute all the commands within the corresponding then keyword. If not, it moves on to the elif keyword and evaluates the subsequent command. This process will repeat until a successful evaluation occurs where all the keywords have been assessed. Pretty cool, right? Another keyword that might come in handy is else. Here's how it fits into our conditional statement. This keyword allows us to define a set of commands that will be executed in the event that all previous evaluations are unsuccessful. Specifically, in the statement that we're looking at here, if the commands next to the if and elif keywords fail, the shell will execute the commands following the else keyword. This provides a fallback option in the event that none of the conditions are met, making our scripts more adaptive to various situations. Handy, isn't it? With the basics of conditional statements under our belt, it's time to dive deeper into the evaluation process itself. You might be wondering, how does the shell determine whether a command was successful or not? The secret lies in something called the exit status. The exit status is a numerical value that represents the outcome of a command, indicating success or failure. To see it in action, let's first execute a simple command. Any command will do, but let's stick with our trusty ls command. No errors here, which means our command was a success. But how is this reflected in its exit status? This is stored in the mysterious question mark variable. To reveal its value, we can use the echo command. This special variable is automatically created by the shell and stores the exit status of the last executed command. Let's give it a shot. Here it is. An exit status of 0 indicates success, while any other number signifies failure. In this case, it indicates that the ls command was executed successfully. Now, let's see what an unsuccessful execution of a command looks like. Let's use the ls command again, but this time, let's ask it to reveal the contents of a directory that doesn't exist. As anticipated, an error occurs. Can you guess what the exit status of this command will be? Let's find out. As mentioned earlier, any value other than 0 indicates an unsuccessful execution, which is precisely what happened here. You might be curious how the value of this variable changes. Commands themselves are responsible for this. Just before a command exits, it updates the value of this variable. If the command breezes through without errors, it sets the value to 0. Otherwise, it assigns any other number. This clever system enables our shell to keep tabs on the success or failure of each command, allowing us to build more robust and intelligent scripts using conditional statements. Now that we've learned the ins and outs of conditional statements, let's apply our newfound skills to a practical example. We'll whip up a script that checks if we're connected to the internet and notifies us accordingly. Let's start by creating a new file with the nano command. From here, let's type out the shebang line. Let the script creation commence. We'll start by using the echo command to inform our users that we're checking for network connectivity. To determine our internet connection status, we'll employ the ping command with a conditional statement. If you recall, ping communicates with a destination to verify internet connectivity. It's similar to how you would attempt to open a website in your browser to confirm that you're connected to the internet. First, let's type the if keyword, followed by the ping command. Along with it, we need to use the C option, which stands for count, and limits how many times the ping command should attempt to communicate with our destination. Without this option, The ping command would attempt to communicate with the destination indefinitely, whereas we only need to check once. To complete our command, we need to specify a destination. For this example, let's simply use google.com. A successful execution means that we're connected to the internet. To designate a set of commands in such an event, let's use the then keyword. Within it, let's notify our users accordingly by using the echo command to display a message. If the ping command fails to reach the destination and throws an error, that means we're not connected to the internet. To specify a set of commands for this scenario, we need to use the else keyword. Within it, let's use the echo command to display a message. Finally, we need to use the fi keyword to wrap up our statement. Our script is now ready. To see it in action, save and exit the file. From here, let's use the chmod command to assign the appropriate permissions. Now, let's see our script in action. Awesome! The ping command successfully communicated with the destination, and our statement executed the appropriate command. Let's try one more time, but this time, let's disconnect our network. You can either unplug your internet cable or specify a non-existent destination within the ping command. Whenever you're ready, execute the script once again. As expected, ping failed to establish a connection, and the commands within our else keyword were executed. Pretty amazing, right? Congratulations! You've now gained a solid understanding of conditional statements and know how to use them to create powerful scripts. Here's a recap of what we learned. Conditional statements evaluate a command and verify its success or failure, executing additional commands accordingly. The shell relies on exit status, a numerical value indicating command success or failure. To determine a command's outcome, the if and elif keywords assess commands, while then dictates the corresponding commands to execute. The else keyword executes commands if all previous evaluations fail. Finally, fi signals the end of the statement. I hope you found this lesson valuable. Until we meet in the next adventure. Welcome to our next lesson. Today, we'll explore the test command. By mastering this tool, we'll be able to create more efficient and flexible scripts. So buckle up and let's dive in. In our previous lessons, we learned that conditional statements evaluate commands and perform actions based on their outcomes. But what if we need to execute a set of commands not based on the evaluation of a command, but rather on the evaluation of various other conditions? For example, we might want to execute a set of commands only when the value of a variable matches a particular number. The test command swoops in to save the day. Designed specifically for use within conditional statements, the test command allows us to evaluate a wide array of conditions, making our scripts more intelligent and adaptable. To showcase this command's versatility, let's kick things off by taking a look at a very simple example. The test command offers several options for evaluating different conditions. Here, we're using the LT command, which stands for less than, to check if the first value is smaller than the second value. Let's give it a go. Notice anything? There's no visible output. This is because the test command is designed to work within conditional statements, and therefore doesn't produce any output. Its primary purpose is simply to provide an exit status. When the condition it evaluates is true, it returns an exit status of 0. Otherwise, it returns a non-zero exit status. Curious to sneak a peek at the exit status? Let's check the value of the question mark variable, just like we learned. As expected, the exit status confirms that our condition is true. 6 is indeed smaller than 9. I double-checked with the calculator. Now, let's switch things up and use the GT command, which stands for greater than, to see if the first value is larger than the second. Spoiler alert, it's not. Time to investigate the exit status one more time. As you can see, we now have a non-zero exit status. This means our condition is false, which makes sense since 6 is definitely not greater than 9. Math wins again. But wait, there's more. Comparing numbers is not the only thing we can do with the test command. It offers a plethora of options that allows us to evaluate a variety of conditions. Let's take a look at them. We'll kick things off with the EQ option, which can be used to determine whether two values are equal. This command checks if the value of the variable named num is equal to 6. On the other hand, we've got the NE option, which determines whether two values are not equal. This version of our command returns an exit status of 0 if the value of the num variable is not equal to 9. Another handy feature of the test command is its ability to evaluate whether our current user has been granted permissions for a specific file or directory. Say hello to the R option, which checks for the read permission. W, which checks for the write permission, and X, which checks for the execute permission. These options help ensure our current user has the necessary permissions before attempting an operation on a file or directory. Want to mix and match multiple conditions? Use the A option, which stands for AND. In this example, the condition will evaluate to true only if our current user has both the read and write permissions for the specified file. Alternatively, we could opt for the O option, which stands for OR. This command will evaluate to true if our user has either the read or the write permission for the specified file. Now that we've laid a solid foundation for the test command, let's build a simple script that puts this newfound knowledge to work. This script will ask for a path and then deduce the type of item provided, be it a file, a directory, or something else. Though simple, it may come in handy at some point. First things first, let's fire up our trusty nano command to create our script. Next, let's type our shebang line. After that, it's time to write the code for our script. Let's start by using the read command to politely ask our users to provide a path. Now, it's time to determine what type of item our users have provided. To do so, we need to use the test command within a conditional statement. Let's start with the if keyword, followed by the test command. To check if the path our users have provided describes the location of a file, we need to use the F command, which stands for file. If the condition evaluates to true, that indicates that the provided item is indeed a file. Let's use the then keyword and the echo command to notify our users accordingly. In the event that an item is not a file, we need to use the LF keyword to determine whether it's a directory. To do so, we need to use the D option within the test command, which stands for directory. Within the corresponding then statement, let's use the echo command to notify our users once more. Finally, if the item is neither a file nor a directory, we'll resort to the else keyword along with the echo command to inform our users that we've stumbled upon a mystery item. Our script is now ready to roll. Before we go ahead and execute it, there's one more thing we can do. I wasn't going to say anything, but conditional statements can be a bit of an eyesore. Let's give them a makeover. Instead of typing the test command directly, we can use two square brackets as a shorthand. Here's what that would look like. The options and arguments for the test command are then placed within the brackets. This syntax is not only easier on the eyes, but also simpler to understand and modify. Just remember to add a space at the start and at the end of the brackets. Otherwise, it won't be recognized by our shell. To tidy things up even more, we can bring the then keyword directly after our command, separating the command and keyword with a semicolon. This nifty symbol is a command separator. It essentially tells our shell that we've typed more than one command or keyword in the same line. By using semicolons, we can make statements easier to read and understand. Lastly, we can introduce a couple of spaces, usually 4 or 5, before the commands that are to be executed. This will make it easy for us to quickly recognize the commands within our statement. Look at that! Quite an improvement, wouldn't you say? Let's exit and save our new script. From here, let's assign the necessary permissions. Now, ladies and gentlemen, it's showtime! Let's execute our script and see it work its magic. As anticipated, the read command prompts us to enter a path. For this example, let's use the script we created in our previous lesson. Awesome! The appropriate command was executed successfully. And there you have it. You now have a solid understanding of the test command and how to use it in your scripts. Let's recap what we've learned this lesson. The test command allows us to evaluate various conditions, returning an exit status of 0 when a condition is true, and a non-zero exit status when a condition is false. The test command provides various options for comparing numbers, variables, and checking file properties, such as specific permissions. To make statements more readable and understandable, we can use square brackets instead of the test command and separate multiple keywords with a semicolon. I hope you enjoyed this lesson, and I can't wait to see you at the next one. Happy scripting! Welcome to another lesson. Today, we'll delve into the concept of for loops and discover how they can help us automate our tasks. Let's dive in. Throughout your journey with Linux, you'll find many of the scripts you'll be required to create will involve the execution of one or multiple commands repeatedly. For example, suppose that you've been entrusted with a task to move, rename, or process hundreds of files. Typing the hundreds of commands necessary for such a task would be a nightmare. That's where the for loop comes to the rescue. For loops work by iterating through a list of items, such as a series of files, and performing an action on each item, such as moving or renaming them. To better understand this concept, let's create a simple for loop using the general syntax as our template. If that looks as clear as a muddy puddle, no worries. Let's break it down. Let's work a bit backwards and start with the in keyword. This specifies the list of items that our loop will go through. This could be a list of file names, an array, or any other sequence of items. For this example, let's keep things simple and use the numbers 1 through 5 separated by a space. Next to the for keyword, we need to specify the name of a new variable, which is often referred to as the loop variable. This variable will be created automatically and take on the value of each item in our list one by one. Since we're playing with numbers, let's call it num. Lastly, we need to tell our loop what to do with each item. Here is where the do and done keywords come in. These define the set of commands that will be executed through every iteration of the loop. Think of them as the bread in a command sandwich. For our example, let's use the echo command to print the value of our loop variable. Now that we've constructed our loop, Let's examine what happens when it's executed. Our loop will begin by taking the first value in our list, which in this case is the number 1, and assigning it as the value of our loop variable. Afterwards, the commands within the do keyword will be executed. In this case, the echo command will simply print the value of this variable. This process will be repeated until no more items are left on our list. This means that our loop will simply print the numbers 1 through 5. Pretty neat, huh? That's the basic idea behind for loops. They allow us to iterate over a predefined list of items and perform a set of actions for each item. Great! You've mastered the basics of for loops. Now, let's get our hands dirty with a real-world example. Picture this. You're drowning in files, and you desperately need to add a prefix to each one to keep things organized. Adding prefixes to similar files can not only help us neatly organize them, but also makes quickly identifying them easier. By creating a simple script that utilizes a for loop, we can automate this mundane task and save valuable time and effort. First up, let's spawn a new file using the nano command. Next, let's declare that our script is written in bash. Now, let's get down to business. Let's begin by using the read command to politely ask our users to input their desired prefix. Next up, the star of the show, our trusty for loop. Let's type the for keyword, followed by the name we want our loop variable to have. Next, let's type the in keyword, followed by the list of items we want to iterate over. In this case, we need to specify every file in our current directory. Now, we could manually type out the name of each file, but who has time for that? Here's a nifty trick we can use instead. Remember command substitution? This awesome technique allows us to use the output of the ls command to generate a list of all the files in the current directory automatically. Within the do and done keywords, let's specify the commands we want to execute for each file. To rename our files, we need to use the mv command. Within it, we need to specify 2 arguments, a source and a destination path. The source will be our loop variable, which, as mentioned earlier, contains the name of a file through every iteration. For the destination path, we need to specify the new name we want each file to have, which will be a combination of our prefix and the current file name. All we have to do is type our prefix variable directly followed by our loop variable. This syntax might seem a bit odd, but it's perfectly valid. Our shell uses the $sign symbol to determine where the name of each variable starts. To make our file names even neater, let's introduce an underscore between the prefix and the name of our file. Now, you might think, easy, we can just add an underscore after our prefix variable. But hold on, this wouldn't work because our shell would misinterpret the underscore as being part of our variable's name. To separate the name of our variable from the underscore, we need to surround it in curly brackets. These brackets tell our shell where the name of our variable begins and where it ends. It's like putting up a no trespassing sign for the underscore. Let's tidy up our loop by using a semicolon to combine a few keywords. Plus, let's add a couple of spaces before our commands. Finally, let's notify our users that the operation has been completed. A simple done will do the trick. With that, our script is now ready. So, let's save and exit the editor. From here, we need to assign the necessary permissions. Drum roll, please. It's time for the grand finale. Let's run our script. In our current directory, The only files present are the scripts we created in previous lessons. So, let's go ahead and use the word script as our prefix. It seems like our script worked. Let's use the ls command to verify. Success! The ls command created a list of all the files in our current directory, and our loop, with the help of the mv command, renamed each file in the blink of an eye. Talk about a dynamic duo. That's the power of automation. And there you have it. You now know what for loops are and how you can use them to automate repetitive tasks in shell scripting. Let's summarize what we learned from this coding adventure. For loops work by going through a list of items and performing an action on each item. This list could be a sequence of numbers, a list of file names, or any other collection of items. To generate a list of items automatically, we can use command substitution, which allows us to retrieve various information from commands and use them within our loop. To separate the names of variables from other sorts of text, we need to surround them in curly brackets. The brackets tell our shell where the names of our variables begin and where they end. I hope you've enjoyed this lesson. Stay tuned for more exciting lessons, and happy scripting! Welcome to this lesson. Today, we'll explore while and until loops, understand their use cases, and learn how to implement them effectively in our code. So buckle up and let's get started. Last time, we learned about for loops, which are fantastic for iterating through sequences, like ranges of numbers and lists of items. Oftentimes, however, we might need to execute a set of commands repeatedly without a predefined list of items. Enter the mighty while loop. This type of loop allows us to continuously execute a set of commands as long as a specified condition evaluates to true. To better grasp this concept, let's take a look at the syntax of a while loop. The while keyword is followed by a condition that will be evaluated. Similar to a conditional statement, our shell will execute this command and check its exit status. If it's successful, the command beneath the do keyword will be executed. This process will repeat until the command being evaluated fails to run successfully. In other words, our loop will only stop when the command next to our while keyword returns a non-zero exit status. Easy peasy, right? Now that we've got the hang of while loops, let's put our shiny new knowledge to the test. One common use case for while loops is continuously monitoring an application to check if it's running. This is useful for ensuring that a critical application runs continuously and that we're notified accordingly. To check if an application is currently running, we can use a command such as PID of, which stands for Process ID of. To see how this command works, let's give it the name of an application. Since we don't have any other applications handy, let's use the name of our shell. This command retrieves the identification number of a process of our choice. Although this information is not directly useful to us, based on whether the PID of command is able to retrieve this information, we can deduce whether our application is running. If PID of is successful, this means that a process with the specified name exists and is currently running. If it returns an error, then we know that the specified application is not currently running. We've resorted to using the PID of command in such a manner because there is no command that can directly tell us if a process is running or not. But hey, where there's a will, there's a workaround. Now that we know how to detect whether an application is running, let's whip up a simple script that keeps an eye on our app and gives us a heads up accordingly. You know the drill by now. Let's start by using the nano command to create a new file. From here, let's type out our shebang line. Time to start typing the commands that'll make our script come to life. First, we'll prompt our users to enter the name of an application to continuously monitor and save it into a variable. Since we want to continuously monitor this application, let's use a while loop along with the PID of command we looked at earlier. As we mentioned before, as long as the command being evaluated runs successfully, our loop will repeat. In other words, in this case, our loop will repeat as long as the PID of command is able to retrieve information related to our application. Just below that, let's use the do keyword to specify the commands that should be executed through every iteration. Here, let's use the echo command to notify our users that our application is currently running. As long as the PID of command keeps getting executed successfully, the commands beneath the do keyword will be executed as well. This process will be repeated until the application we specified crashes or otherwise stops. In that case, the PID of command will fail to retrieve the appropriate information and return an error. Our shell will then ignore the commands beneath the do keyword and move on to the rest of the commands within our script. Here, we can use the echo command to notify our users that our application is stopped. Great! Our script is ready. Or is it? While this script would technically work, it would also crash our computer. The thing about loops is that they don't have a speed limit, which means that as long as the command they evaluate runs successfully, they'll repeat as fast as our system's hardware allows. This can lead to loops consuming 100% of our system's resources and might even result in our computer crashing. To alleviate this problem, we need a way to limit how fast our loop repeats. This is where the sleep command comes in handy. This command instructs our shell to wait a specified number of seconds before continuing. In this example, let's make our shell wait for 5 seconds. It's crucial to be mindful of a loop's execution rate when working with loops. Nobody wants a computer meltdown. Now, our script is genuinely ready. Let's save and exit. From here, let's assign the necessary permissions and execute our script. Since we don't have a real app to test, we'll use our shell again. Awesome! Our script works like a charm. The PID of command keeps getting executed, and as long as it retrieves the app's ID, our loop continues. When and if it stops, we'll be notified. Fingers crossed that doesn't happen though, because we need our shell to keep functioning. But don't go anywhere just yet, because there's more to discover. Let's dive into another type of loop called until loops. Here's what it looks like. Unlike while loops, which execute a set of commands as long as a condition is true, until loops do the exact opposite. They execute a set of commands as long as a condition is false. This means that the corresponding commands under the do keyword will continue to be executed as long as the command next to our until keyword runs unsuccessfully. Until loops are often used for validating user input. Here's a simple example. This loop ensures that our user enters one of two options when prompted, either yes or no. If our user enters any other value, the loop will repeat until our user enters a valid input. Here's how it works. This loop uses the test command to check whether the value of the input variable is equal to either yes or no. So far, we haven't created any such variable, which means that the test command won't be able to check its value. In other words, the test command will fail to run successfully, which will cause the corresponding commands beneath the do keyword to be executed. In this case, the read command will prompt our user to enter the value for a new variable. After our user enters a value, the input variable will be created with the appropriate value. At this point, our condition will be evaluated once again. If the user entered a value of either yes or no, the loop will stop. Otherwise, the loop will repeat until the user enters a valid input. Pretty cool, right? And that's a wrap. You are now a pro at both while and until loops. Let's recap what we learned. While loops allow us to repeatedly execute a set of commands as long as a condition evaluates to true. Once the condition evaluates to false, our loop will stop executing. Until loops are the opposite of while loops. Unlike while loops, which repeat a set of commands as long as a condition is true, until loops repeat a set of commands as long as a condition is false. When working with loops, remember to use the sleep command to limit the rate at which your loop repeats. This command simply tells the shell to wait a specified number of seconds before continuing. I hope you had a blast in this lesson, and I'll catch you in the next one. Welcome to this lesson where we'll be exploring how to make scripts accept arguments and options. Buckle up and get ready to level up your scripting game. Scripts often need a little something from the user, such as the name of a file or the path to a directory. While we could use the read command to prompt for input, a more efficient way would be to pass arguments and options directly to the script, just like we would with a command. To demonstrate, let's whip up a quick and dirty script that accepts a path and determines whether it corresponds to an existing item. To kick things off, let's use our trusty nano command to create our new script. From here, let's type out our shebang line. And now, let's type the commands that will bring our script to life. First things first, we need to accept an argument. Here's how we can do that. Our users will provide a path by specifying it as an argument right after our script's name, just like they would with any command. Our shell will then automatically create a variable named 1 that will store the value of the first argument that was provided. This variable is named 1 because it contains the first argument that was passed to our script. A second argument would be stored in a variable named 2, the third in a variable named 3, and so on. Easy peasy, right? But we're not done just yet. When it comes to scripts that require arguments to function, it's essential that we check if an argument was actually provided. It's like checking if you have your keys before leaving the house. After all, our script wouldn't be able to function without our users specifying a path. Thankfully, our shell provides us with a special variable denoted by a hashtag that represents the number of arguments passed to our script. Since our script only requires a single argument, we need to make sure it politely refuses to continue unless the value of this variable is equal to 1. How do we do that, you ask? Well, remember our old friend, the test command from the previous lessons? We're going to use it within a conditional statement. For our condition, we need to use the NE option, which stands for not equal. In case the number of arguments passed to our script is not equal to 1, we need to notify our users accordingly. Let's also use the exit command to terminate the script outright. As an argument, we need to specify a number that represents the exit status of our script. Remember, 0 indicates success, while any non-zero value signals an error. In our case, we need to use a non-zero value, such as 1, which is like saying, "Oops, something went wrong." Now that we've verified that an argument was provided, our next step is to determine whether the specified path corresponds to an existing item. I mean, that is kind of the whole point of our script, isn't it? To achieve this, we need to create another conditional statement. Within it, let's use the test command along with the E option, which stands for exists. In the event that the item does exist, let's use the echo command to cheerfully inform our users. If the item doesn't exist, let's use the else keyword, along with the echo command once again to gently let them know. Great! Our script can now determine whether a specified path corresponds to an existing item. This brings us a step closer to a sophisticated and efficient script that handles user input like a pro. But why stop there? Let's take it up a notch, shall we? Let's also make our script accept an option that, when specified, displays a message informing our users about the arguments and options that our script accepts. Let's name this option H, short for help. The code that breathes life into this functionality should be placed before checking if an argument was provided. Why, you ask? Well, our users might want to view the information that this option provides without actually using our script. After all, who doesn't like a good sneak peek before the main show? To make this happen, we need to use the getOpts command, which stands for get options. True to its name, this command simply determines which options were passed to our script. To execute a set of commands accordingly, we need to use it within a conditional statement. So, let's start with the if keyword, followed by the getOpts command itself and the option we want to accept. In the event that our users specify this option, the getOpts command will be executed successfully. If not, it will return a non-zero exit status, signaling failure. The getOpts command also requires that we specify the name of a new variable. This variable will store the name of the option that was found. This comes in handy in situations where our script accepts more than one option, and we need to determine which option was found by the getOpts command. We'll see what that looks like in just a bit. Within our conditional statement, let's use the echo command to display a message detailing how this script can be used. Since it's clear that our user wanted to check the script's syntax rather than to use our script, let's use the exit command to terminate its execution. For our exit status, let's use the number 0 to indicate that our script completed its intended task successfully. Even though our script is ready to go, let's explore a few more ways to accept options, just so we can equip you with some extra skills. One such scenario involves accepting option arguments, which are arguments for specific options. Here's how we can achieve that. The following statement is quite similar to the previous one, but there's a subtle difference. After the name of our option, we've added a colon. This tells the getOpts command that this option necessitates an argument. The value of this argument will then be stored within the optarg variable, which is short for option argument. In this example, the echo command is used to display its value. Pretty cool, right? On other occasions, we might need to make our script accept more than one option. Once again, we've got you covered. In this example, a while loop iterates through all the options that getOpts finds. Here, getOpts is on the lookout for two options, A and B. It will keep getting executed successfully with every option it encounters. The opt variable then stores the name of the discovered option. And through a conditional statement, we can execute a different set of commands depending on the option. How cool is that? However, our current script doesn't require any of these fancy complexities. So, let's trim away the extra code like a hairdresser giving a neat haircut. Now, with our script looking sharp and ready, let's save our masterpiece and exit the editor. Next, let's give our script the necessary permissions. Now, it's showtime. Let's execute our script. Don't forget to specify a path as an argument, just like you would with any command. Fantastic! Our script functions as intended. Let's put our script to the test once again, this time using the H option. And what do you know? Our script is still performing beautifully. It looks like we're becoming quite the experts at this whole scripting business. The possibilities are endless. And there you have it, folks. You now possess the knowledge to make your scripts accept arguments and options like a pro. Here's a quick recap. Passing arguments or options to a script is a convenient and efficient way for users to provide input without needing to interact with the script during its execution. The shell automatically creates several variables that hold the value of each item that was passed to the script. The first argument is stored in a variable named 1, the second in a variable named 2, and so on. To determine which options were passed to a script, use the getOpts command. GetOpts stands for Get Options, and it interprets the options that were passed to a script. I hope you enjoyed this lesson as much as I enjoyed teaching it. I'll see you at the next one, and until then, happy scripting. Keep being awesome. Welcome to another lesson, my fellow knowledge seekers. Today, we're going to explore input redirection, which is a powerful way to provide input to commands in Linux. Let's see how it works. In Linux, commands serve as versatile tools that help us interact with data and manipulate files. To work their magic, commands need to retrieve and display various types of information. For instance, consider the cat command, which reads a file's contents and presents them in our terminal. The information fetched by commands is referred to as input, while the information they produce is known as output. In essence, the cat command takes a file's content as input and displays it as output in our terminal. Throughout this and the following lessons, we'll explore the mechanisms that allow commands to receive and send information, as well as how we can manipulate them in various ways. First up, let's explore how commands receive input. Picture this. You've been handed a file that contains hundreds of URLs with items that need to be downloaded. This is actually something that's likely to be required of you. Downloading items from a list is a relatively common task. This could be a list of software packages, documents, or any other type of file. To demonstrate how this can be done, we'll first use the nano command to create a file that will store a few download links. We don't actually need to download any files, so let's just type a few random download links. Now, save and exit. With our file ready, let's see how we can download every item stored within it. The most obvious approach is to simply type each link after the wget command. However, depending on the number of links, this can get painfully tedious. But wait, there is a way to accomplish this task without completely losing our mind from all that manual typing. Say hello to input redirection. Instead of manually feeding input to the wget command, we can direct it to fetch all the URLs from our file. It's like giving your command a shortcut to the data it needs. To do so, all we have to do is type the wget command, followed by the less than symbol and the name of our file. The less than symbol channels the contents of our file into the wget command. This symbol is not an argument or an option. It simply tells our shell to pass the contents of this file into the wget command. Let's try it. Success! The contents of our file were read correctly, and the wget command attempted to download all the items from the links we specified. Obviously, the links we used didn't correspond to actual websites, so the wget command returned empty-handed. Nevertheless, this shows that the wget command was able to read the contents of our file. How cool is that? Now that we've got the hang of input redirection, let's dive deeper into its inner workings. Imagine the components that make up our operating system, such as the terminal, our shell, and the commands we execute within them. For these components to function properly, they need to send and receive information. For instance, every keystroke in our keyboard needs to be transmitted to the terminal so that it can be displayed on our screen. This is where streams come into play. Think of streams as communication channels that allow the various components of our operating system to send and receive information as needed. They're like communication highways that enable the exchange of data. When our shell springs to life, it sets up several of these streams to handle all this juicy input and output. The first of which is the standard input stream, or stdin for short. As the name suggests, the components within our operating system use this stream to retrieve information. By default, the source of this stream is our keyboard. Our terminal relies on this stream to capture every keystroke from our keyboard and display it on the screen. Input redirection alters the source of this stream, allowing the various system components to retrieve information from different sources. In our previous example, the shell changed the source of the standard input stream from the keyboard to the specified file so that the wget command could access its contents. Next in line, we have the standard output stream, or stdout. As the name suggests, this stream sends information to destinations such as files, printers, or USB drives. By default, the destination of this stream is our terminal. When we execute a command, the generated output is sent to this stream. Since the destination of this stream is the terminal, the output is displayed to us. We can use a technique called output redirection to change the destination of the stream, which we'll explore in the next lesson. Last but not least, we have the standard error stream, or stderror for short. As the name suggests, this stream is used to send error messages and diagnostic information. By default, the destination of this stream is our terminal. Any error messages generated by our commands are sent to this stream. Since the destination of this stream is the terminal, error messages are displayed accordingly. Error messages are not fundamentally different from other types of output. However, separating error output in such a manner allows us to handle it differently. We'll see what that looks like in a following lesson. To better understand how these streams work, let's pull back the curtains and explore exactly what happens when we execute a command such as wget from our previous example. The moment we hit enter, the shell receives our command from the terminal through the standard input stream and starts interpreting it. Upon recognizing the less than symbol, the shell changes the source of the standard input stream to the specified file instead of the keyboard. This ensures that when the wget command tries to retrieve information from this stream, it receives the contents of the file. The rest of the streams remain unchanged, meaning the destination of both the standard output and the standard error streams is the terminal. With the streams properly configured, the shell executes the appropriate file, and the wget command takes control. In this case, since no arguments were provided, the wget command retrieves information from the standard input stream. After obtaining the file's contents, it downloads the specified items accordingly. Throughout this process, the generated output is sent to the standard output stream, which is connected to the terminal. Consequently, progress messages or other output from the wget command appear on the terminal. If the wget command encounters errors, the corresponding messages will be sent to the standard error stream, which is also connected to the terminal. This ensures that any error messages or diagnostic information are displayed on the terminal as well. And that's exactly how commands use streams to send and receive information. How cool is that? That's not to say, however, that all commands accept input from the standard input stream. Some commands only expect input in the form of an argument. The mkdir command is a perfect example of this. To illustrate this, let's whip up another file using the nano command, this time to store the names of a few directories we want to create. Now, let's type down a few random directory names like so. Now, let's save and exit. To create every directory listed within this file, let's try using input redirection just like before. Oops! An error message popped up, complaining that we didn't specify any arguments. The mkdir command is picky and doesn't retrieve information from the standard input stream. It only expects input in the form of an argument. Thankfully, we have a trick up our sleeves. Allow me to introduce you to the xargs command, which stands for extended arguments. This versatile command reads input from standard input and uses it as an argument for the command of your choice. Think of xargs as a magical translator that helps commands understand input from the standard input stream. All we have to do is type xargs followed by our command. The xargs command will process the file's contents and pass each directory name as an argument to the mkdir command. Here's an example of the command it would end up executing. This allows us to create all our directories at once. Let's put it to the test. But how can we be sure it worked? Let's summon the ls command to verify. Awesome! As you can see, all the directories in our file have been created successfully. By using xargs, we can pass various types of input to commands that wouldn't usually accept input redirection. And there you have it. You've mastered input redirection and discovered a valuable workaround for commands that don't support it. Here's a quick recap. Data streams enable scripts, commands, the terminal, and the shell to receive input and send output. The shell sets up 3 streams by default: standard input, standard output, and standard error. Input redirection allows us to change or redirect the input source of a stream, which is particularly useful for automating the process of providing information to a command. Some commands don't accept input from standard input. The xargs command comes to the rescue, reading the standard input stream and converting it into arguments for those commands. I hope you've enjoyed this lesson, and I can't wait to see you in the next one. Welcome to another lesson. Today, we'll dive deep into the world of output redirection. This powerful technique allows us to take control of where a command's output is displayed. Let's jump right in. As you are well aware by now, working within Linux typically involves executing commands and squinting at the information they produce. Oftentimes, however, the output generated by a command can be quite extensive, and it might not always be convenient to have it displayed on our screen. Instead, we might want to save the output into a file, whether that's for future reference or further processing. This is where output redirection comes to the rescue. Output redirection allows us to capture and redirect the output of a command into a file, instead of displaying it on our screen. To demonstrate, let's see how we can save the output of the ls command into a file. All we have to do is use the greater than symbol, followed by the name of a new file. The greater than symbol is not an argument or an option for the command. Instead, it instructs our shell to send the output to a file rather than our terminal. Give it a go and you'll see nothing on your screen. Why? That's because the output of this command has been redirected into the file we specified. To verify, let's examine the contents of our new file. And here it is. The output of the ls command has found a new home in our file. Neat, huh? But how exactly does this sorcery work? The moment we press enter, the shell recognizes the greater than symbol and changes the destination of the standard output stream from our terminal to the file we specified. As a result, any output generated by the command is sent there instead of being displayed on our terminal. It's like a magical portal that transports the output from one place to another. Now that we've got a handle on this whole output redirection business, let's dive into the fun part, figuring out all the ways we can use it to our advantage. One command whose output might be worth saving is the last command, which displays a list of the users that most recently logged into our system. Let's put it to work and see what it can do. What we see next is like a digital guest book. Next to each username, we can see various details, such as when logins occurred, how long the users were logged in for, and other relevant information. This data can be invaluable for monitoring user activity and identifying unauthorized access attempts. So, it's only logical we'd want to preserve this information in a file. And thanks to our trusty friend, the greater than symbol, it's as easy as pie. Let's try our command and see it in action. To ensure that our redirection worked, we'll summon the cat command. Fantastic! We've successfully stored the output of the last command. This allows us to maintain a record of all the users who have logged into the system and help track user activity, spot patterns, and pinpoint potential security issues. How cool is that? Another command that benefits from output redirection is du, which is short for disk usage. This command provides a breakdown of every item in our current directory, sized up in kilobytes. The catch? The list can be quite extensive, especially when we're dealing with hundreds of files and folders. Output redirection to the rescue. By saving the output to a file, we can decipher it at our leisure. And to make things even neater, let's throw in the H option, which stands for human readable, and instructs the du command to display sizes in units such as k for kilobytes or m for megabytes. With our command ready, let's see it in action. It seems like it worked. Let's use the cat command to check out our new file. And there you have it. By storing the output of the du command, we can process the data more efficiently and at our own pace. This even allows us to perform more complex operations using other commands. For instance, we could sort, filter, or manipulate the data in different ways to extract specific information or present it in a more digestible format. We'll get into the juicy details of that in a following lesson. But wait, there's more. Another practical application of output redirection is saving the output of the ps command, which we explored in one of our earliest lessons. If you need a quick refresher, the ps command displays a snapshot of all the processes running on our system, along with various details about them. Remember the E and F options? They stand for everything and full format respectively, and they instruct the ps command to display every process in our system in a format that includes more information. Instead of merely saving the output of this command into a file, let's kick it up a notch and create a script that does so automatically at regular intervals. It's like keeping a diary, but for the processes on our computer. This comes in handy for tracking processes over time and identifying issues caused by troublesome processes or system resources. For instance, if we notice a sudden increase in CPU or memory usage, we can refer to the recorded data to pinpoint the problem. So, let's roll up our sleeves and get to work. You know the drill. Let's begin by creating a file using the nano command. From here, let's type out the shebang line, and let's type the code that'll make up our new script. First things first, let's create a variable to store the path of our new file. This will allow us to easily reference the path throughout our script. Next, we need to create a loop that repeats indefinitely. To do so, we can use a while loop, along with the test command and a condition that always evaluates to true. Here's what that would look like. Since 1 will always be smaller than 2, our loop will repeat indefinitely. Math for the win. But wait, there's an even more elegant solution. The true command. Living up to its name, this command simply returns an exit status of 0 whenever it's executed. Inside the loop, we need to use the ps command to generate a list of processes. But here's the twist. To redirect its output, we need to use 2 consecutive greater than symbols instead of just 1. That's because a single greater than symbol would overwrite or replace the contents of our file each time we use it. This means that instead of keeping a record of the processes in our computer, the single greater than symbol would delete all previous entries before adding new information. Not exactly what we want. On the other hand, 2 consecutive greater than symbols tell our shell to append or add to the existing contents of our file instead of replacing them. This ensures that new information is added at the end of our file each time the loop runs, while also preserving the previous entries. To sprinkle the date into our snapshots, we need to redirect the output of the echo command as well. To get the current date and time, we need to use command substitution along with the date command. Let's not forget to make our shell wait between each iteration of the loop by using the sleep command, just so we don't crash our computer. Our script is now ready to roll. Let's save our masterpiece and exit the editor. From here, let's assign the necessary permissions using the chmod command. Now, let's execute our script and let it run for a while. After a few seconds, hit Ctrl and C to stop the action. To confirm that our script was successful, let's examine the contents of our log file. Behold! Our script has captured a series of snapshots, complete with the corresponding date and time. Isn't output redirection great? Give yourself a pat on the back. You've just mastered the art of output redirection. To recap, here's what we've learned. Output redirection is a powerful tool that allows us to capture and redirect the output of a command to a file. This is particularly useful for output that requires further processing or might be beneficial for future reference. The greater than symbol alters the destination of the standard output stream from the terminal to a specified file. This ensures that any output produced by our command is redirected to that file. Keep in mind that using a single greater than symbol will overwrite the contents of a file each time it's used. To avoid losing data, use two greater than symbols consecutively to append or add new information to the existing contents of a file. I hope you've enjoyed this lesson, and I'll catch you in the next one. Welcome to another lesson. Today, we're going to explore the concept of error redirection and learn how to use it effectively. Let's dive right in. In our previous lesson, we learned how to direct the valuable information that commands produce and save it into a file. However, apart from regular output, commands also display errors, warnings, or other diagnostic information. Take the ls command, for instance. When we attempt to view the contents of a non-existent directory, we're greeted with a lovely error message. In Linux, error output such as this is handled differently than regular output. While regular output is sent to the standard output stream, error output is directed to the standard error stream. This distinction allows us to isolate error messages and address them individually. Want to see this in action? Let's save the error output of the ls command into a file. All we have to do is type the number 2, directly followed by the greater than sign, and the name of a new file. By using this syntax, we're instructing the system to redirect the standard error stream to the specified file instead of displaying it on the terminal. Let's give it a shot. The ls command most likely returned an error, but due to the redirection, it doesn't appear on our screen. Let's shine a light on it using the cat command. Success! The error message has indeed been successfully saved in our file. This nifty trick makes identifying problems and troubleshooting issues a breeze. This proves particularly useful for debugging applications, scripts, or keeping a detailed log of any issues. You might be wondering, where does the number 2 come from in the name of this redirector? Is it because we programmers love even numbers? Not quite. To figure this out, we must first learn about something called file descriptors. In Linux, each stream is assigned a unique identification number, with the standard input stream typically assigned the number 0, the standard output stream assigned the number 1, and the standard error stream assigned the number 2. These identification numbers, known as file descriptors, help the shell distinguish between different streams. So, The number 2 in our redirector signifies that we want to redirect the contents of the standard error stream, which is assigned the file descriptor 2. But why are they called file descriptors? In the realm of Linux, everything is represented in the form of a file, including the kernel, devices, and streams. As a result, the identification numbers assigned to these files, including those representing our streams, are referred to as file descriptors. And there you have it, a crash course in file descriptors. Now that we know how error redirection works, it's time to roll up our sleeves and put our newfound skills to the test. Consider this scenario. You're feeling ambitious and decide to install 3 applications at once. Here's the command you'd use. Should any errors or warning messages arise during installation, they'll be redirected to a file named installation errors. Let's give it a go. As the applications get installed, a plethora of information floods our terminal. This is where error redirection truly shines. As you can imagine, without error redirection, if any errors were to appear during this process, they would be rapidly pushed out of sight. By capturing and storing error messages separately, we can effectively isolate them from the overwhelming output. This allows us to easily locate and review them later. Now that our applications have been installed, let's examine the contents of our new directory to see if any warnings or error messages were encountered during this process. No output. This indicates that the apt-get command did not encounter any errors. That's like finding an empty cookie jar. A bit disappointing, but mostly a relief. Rest assured, however, if there had been any errors, they would have been captured and saved within this file, which would allow us to examine them much more efficiently and systematically. Pretty cool, right? Here's a handy tip. Using the double greater than symbol allows us to append or add to the existing contents of a file. Here's what that would look like. With this command, any error messages generated by the apt-get command will be appended to the installation errors file instead of overwriting it. This is particularly useful for maintaining a running log of errors or analyzing multiple error messages simultaneously. These logs can be reviewed periodically to track recurring issues or identify trends, helping improve the overall stability and reliability of the system. Pretty neat, huh? But wait, there's more. Sometimes you'll want to capture both regular and error output at once. This is especially useful for when we need to capture all the information generated by a command. One command that generates useful information on both streams is the ping command. Errors generated by this command can offer valuable insights into network connectivity problems or other encountered issues. To capture both regular and error output from the ping command, we need to use an ampersand, directly followed by the greater than sign. This redirector combines both standard output and standard error streams and redirects them to a file of our choice. Let's give it a go. As expected, our terminal stays quiet. But let's sneak a peek at our new file. Awesome! The entire output of the ping command has been saved in this file. While no errors were encountered in this case, having both types of output in a single file simplifies the identification and troubleshooting of network issues. It's worth noting that another redirector that achieves the same result is the following. The numbers in this redirector refer to the file descriptors of each stream. The redirector combines the standard error stream with the standard output stream, and then redirects the combined output into our file. Essentially, it performs the same function as the ampersand redirector. We mention this syntax because you might encounter it in scripts or online examples. Alright, enough with the technical stuff. Let's have a blast exploring the apps we installed earlier. First up is Fortune, which displays random quotes, jokes, or other humorous snippets on the command line. It's your go-to for a quick laugh or to add some spice to your terminal sessions. Next is SL, which shows a charming train animation when you accidentally type SL instead of LS. While it's not exactly practical, it certainly adds a dash of charm to your command line interactions. Finally, we have LOL Cat, a colorful twist on the cat command that sprinkles rainbow effects on text output in the terminal. It's perfect for making your scripts pop or just adding a little color to your day. Once you're done playing around, feel free to uninstall these apps. And there you have it, folks. You've now mastered error redirection and its practical applications. A quick recap. Error redirection captures and stores error messages generated by a command into a file. This makes tracking important information and referencing it at a later time easier, as well as maintaining a running log of errors. Each stream in our computer has a unique identification number known as a file descriptor. The standard input stream is typically assigned the number 0, the standard output stream is assigned the number 1, and the standard error stream is assigned the number 2. To redirect error output, use the number 2 followed by the greater than symbol. Similarly, to redirect both error and regular output, use an ampersand followed by the greater than symbol. I hope you've enjoyed this lesson and found it informative. Stay tuned for the next one, and happy learning! Welcome everyone! In this lesson, we'll explore the concept of command piping and how to use it to process and manipulate data within the command line. Let's dive in. Remember in a previous lesson when we discovered how to redirect the output of a command into a file? Well, today we're going to kick it up a notch. Let's see how we can sort, filter, or search for specific patterns within that output. Picture this. You need to identify which files in your current directory are consuming the most space. Knowing which files are the largest can help free up disk space, optimize system performance, and troubleshoot issues related to disk space usage. To achieve this, we need to use the du command, which we learned about in our previous lesson. The H option makes the output more user-friendly by displaying sizes in a human-readable format, such as K for kilobytes or M for megabytes. From the output, we need to pinpoint which files are taking up the most disk space. The most straightforward option would be to simply search through the output until we find them. However, depending on the number of files in our directory, this could end up being a very tedious task. It would be like searching for a needle in a haystack, and who has time for that? Luckily, there's a solution. We can use the sort command to automatically arrange the output of the du command so that the largest files appear at the bottom of the list. This will allow us to quickly and easily identify which files are consuming the most disk space, without the need for the manual labor. To accomplish this, we need to pass the output of the du command into the sort command. One way to do this is to use an output redirector to save the output of the du command into a file. Afterwards, we can use an input redirector to pass the contents of our new file into the sort command. When working with the sort command, it's important that we consider the data we have and how we want to sort it. In this case, the du command generates a list of files with sizes specified in the human-readable format, such as K for kilobytes or M for megabytes. To ensure that the data is sorted correctly, we need to use the H option within the sort command as well. This option tells the sort command that the data we're providing is in the human-readable format we mentioned earlier, and ensures that it will be sorted correctly. It's like giving sort a pair of glasses so that it can read the format correctly. Let's put it to work. Awesome! Now the largest files in our directory appear at the bottom, and identifying them is as easy as pie. But wait, while saving the output of the du command to a file works perfectly well, there's a more efficient way to accomplish this task. Allow me to introduce you to command piping. With this technique, we can pass the output of the du command directly as input to the sort command. The pipe symbol takes the output from the du command and feeds it directly into the sort command, eliminating the need for saving and reading files. Think of it as a temporary storage area for data that's being passed from one command to another. In other words, it does exactly what we did previously with our file, only a lot faster. Command piping essentially automates this process and makes it more efficient. It's a neat way to manipulate and process data within the command line that can save valuable time and effort. Now, you might be wondering, why not just use an output redirector instead of a pipe? For example, wouldn't this command work just as well? Well, as tempting as it may seem, this command wouldn't work as intended. In fact, it would fall flat on its face. Instead of piping the output to the sort command, it would redirect the output to a file named sort. The issue is that the sort command requires data from the standard input stream, but our output redirector only modifies the destination of the standard output stream. On the other hand, the pipe symbol sends the output of the du command as input to the sort command through the standard input stream, allowing it to receive and process the data. So, while the output redirector and pipe symbol may appear similar, they serve different functions. Now that we know how piping works, let's put our skills to the test with another example. Remember our old friend, the ps command? It's often used for figuring out which processes are consuming the most CPU resources. To make it display information about the CPU usage of each process, we need to use the A, U, and X options instead of the usual E and F. A stands for all and tells the ps command to list the processes for every user on the system. U instructs it to provide additional information about each process, including their CPU usage. And X makes it include background processes as well. Let's try it. And here it is. But who wants to go through all this data to pinpoint which processes are eating up the most resources? Not us, of course. Instead, we can use the sort command once again to sort the output. As with our previous example, we need to consider the type of data we have and how we want to sort it. Since the output of the ps command contains many columns, we need to specify which column we want to sort. In this case, we'll sort based on the third column, which displays CPU usage of each process. To do this, we need to use the K option, which stands for key, followed by the number 3, which specifies the third column from the output. But we're not done quite yet. Since the CPU column contains numeric values, let's also throw in the N option. This option ensures that the values of the CPU column are sorted based on their numerical values rather than alphabetically, which is the default sorting method for the sort command. Now that we have our command, let's try it out. Brilliant! Our output is now sorted based on each process's CPU usage. This can be incredibly useful for monitoring system resources and troubleshooting performance issues. Granted, in this specific case, none of our applications are consuming significant resources, but this may differ in other scenarios. But why stop there? We can refine the output of the sort command even further by introducing another command to the mix, such as head or tail. Let's start with the head command, which is just as exciting as it sounds. As the name implies, this command can be used to trim the output so that only a few lines appear. The 3 option specifies that only the first 3 lines of the output should be displayed. Since the most resource-hungry applications appear at the bottom, this command shows the ones using the least CPU, allowing us to quickly identify them without clogging our terminal. Alternatively, we can use the tail command to display the last few lines in our output. Once again, the 3 option specifies that only the last 3 lines should be displayed. By using this command, we can view only the applications that are consuming the most CPU. This makes identifying resource-hungry applications a breeze. Congratulations! You've now mastered the art of command piping. Here's a quick recap. Command piping is a powerful technique that allows us to pass the output of one command as input for another command. The pipe symbol serves as a connection between 2 commands. It takes the output generated by one command and seamlessly sends it as input to the next. This makes it a powerful and flexible way to manipulate data. Using the sort command in combination with a pipeline, we can efficiently analyze and process large amounts of data. I hope you enjoyed this lesson, and I can't wait to see you at the next one. Welcome to another lesson. Today, we're going to explore the grep command and learn how to use it to save valuable time and effort. Let's dive right in. Working in Linux can sometimes feel like detective work, as you'll often be required to extract specific information from the output of a command or the contents of a file. Picture this. You've been tasked with finding out the version of an application running on your system. This task is relatively common in Linux, and is one you'll likely be required to do at some point or another. The most straightforward way to find out about an application's version is by using the dpkg command, which we covered in a previous lesson. To list details about every package on our system, we'll include the L option, which stands for list. But be prepared, it's like opening the floodgates of information. To find the information we need, we can just scroll through the output until we find our package. But let's be honest, who has the time or the patience for that? Especially when we have hundreds or even thousands of packages installed. With so many packages, even sorting the data might not be sufficient. This is where the grep command comes to the rescue. If you've worked with Linux for any length of time, you've probably bumped into this little gem. grep stands for Global Regular Expression Print. But don't let the fancy title scare you. It's just a complicated way of saying that it searches for a specific word and displays every occurrence. In our case, to check for an application's version, we can pipe the output of the dpkg command into grep, followed by the term we want to search for. Here it is! The application's version has now appeared. The grep command searched through the output, found every occurrence of the specified word, and displayed it on our terminal. Do you see how powerful grep is? With a single command, we can use it to retrieve information we need quickly and efficiently. Now that we understand how grep works, let's see it in action again. One common use case is searching for text within log files. These files store records of system events, application behavior, and user activities. Basically, the nitty-gritty details of your Linux system. By analyzing log files, we can troubleshoot problems, monitor security issues, and evaluate our computer's performance. Think of it as a peek behind the curtain of our Linux system. Log files in Linux are stored in the /var/log directory. So, let's start by navigating there. This directory contains various log files, but let's focus on the most important ones. The crown jewel among them is the syslog file, which records every event that occurs when our system is in use. Think of it as the black box of our Linux system. This wealth of information can help us troubleshoot issues, monitor system performance, and identify security threats. If you find that your syslog file is missing, which can happen in some older WSL installations, we've got you covered. We've created a simple syslog file that you can download using the wget command. The link is also available in the description for easy copy-pasting. Ready to dive into the syslog file? Let's take a look. Don't worry if most of it looks like gibberish. It's not meant to be easily decipherable unless you're a specialized Linux technician. That's where the grep command comes in to save the day. It can help us make sense of this file by extracting only the information we need. For instance, by searching for the word sudo within this file, we can discover information related to which user tried to use the sudo command, which command they executed, and whether they were successful or not. To do so, let's type grep, followed by the search term, in this case sudo, and the path to the syslog file. Awesome! All information related to the use of the sudo command appears. In this case, password authentication failed, and poor John couldn't execute the apt-get update command. Such information is invaluable for detecting security threats and identifying misbehaving users or applications. Let's crack open another secret diary of our Linux system, the auth.log file. This file keeps track of every login attempt on our system. Once again, if you're using a WSL installation, this file might be playing hide-and-seek with you. Don't worry though. We've created an example you can download using the following link. All set? Let's examine the contents of this file. If the content seems like ancient hieroglyphics, don't sweat it. What we're looking for is information about unauthorized login attempts. This is where grep comes in handy once more. Let's use the grep command to search for the phrase failed login within this file. This time, we'll use the I option, which stands for ignore case. This will make sure that grep doesn't discriminate between uppercase and lowercase letters. And since our search pattern contains a space, we must also enclose it in quotes. And there you have it. All entries related to failed login attempts have been displayed. The I option was necessary because the phrase failed login appears in uppercase within the file. By examining the output, we can determine whether any unauthorized login attempts were made on our system. This information is invaluable for quickly and easily identifying potential security threats. Curious about the number of failed login attempts on your system? grep has got us covered with the C option, which stands for count. Instead of displaying the lines containing our pattern, grep returns the number of times our pattern was found. This is perfect for a quick and easy tally of all the authentication failures on our system. But wait, there's more. Another powerful use of the grep command is searching for a word within multiple files at once. For example, we might want to search for the word error within all the log files in this directory. To do this, we need to use the R option, which stands for recursive. And just like that, every line featuring the word error from every file in our current directory has been displayed. This information allows us to identify and resolve potential issues quickly and efficiently. Give yourself a pat on the back. You've now learned what the grep command is and how to use it effectively. Let's recap what we covered in this lesson. The grep command can search for a specific word within the output of a command or the contents of a file and display every occurrence. One common use case is searching for text within log files. Analyzing log files with grep helps us troubleshoot problems, monitor security issues, and evaluate computer performance. Using the I command to ignore the case of search patterns, C to count the occurrences of the pattern, and R to search for a pattern within all the files in the current directory. I hope you've enjoyed this lesson as much as I have. I can't wait for our next adventure in the land of Linux. And so, we've arrived at the conclusion of our Linux command line course. We hope that you've gained the skills and confidence to tackle a wide range of tasks using Linux efficiently and effectively. As you continue your journey with Linux, remember that practice and curiosity are key to becoming proficient in the command line. The Linux community is vast and supportive, offering countless resources and forums for further exploration and troubleshooting. Embrace the open source spirit, and don't hesitate to contribute to the community by sharing your knowledge and discoveries. Once again, congratulations on completing this Linux command line course. Your newfound skills will serve you well in the ever-evolving world of technology. May your journey with Linux be rewarding and filled with endless opportunities for growth and exploration. Teaching you has been an absolute pleasure, and we hope you've enjoyed the journey just as much as we have. Your feedback is invaluable to us, so please take a moment to share your thoughts through a review. We look forward to seeing you in our next course. In the meantime, keep exploring the power of the command line and expanding your skill set. Until we meet again, we bid you farewell and wish you happy coding.